everyone, and welcome to another video. So today I'd like to have a comprehensive end-to-end discussion about launching a high-altitude weather balloon. As we'll see, this is a fairly large project that involves building custom hardware components, writing specialized software, planning a flight operation, analyzing loads of data, and many other tasks. So we're going to cover every step in the process in this video at a fairly high level, and we've made separate standalone videos to discuss some of these subcomponents in greater detail. I'll include timestamps and links to those videos in the description of this one. So in general, we're going to break this discussion into 4 parts. So number 1, we're going to talk a little bit about the flight vehicle. So this is talking about the actual hardware and software components that we're going to be flying on our high altitude balloon, mostly in the payload box. The second part of this video is going to cover mission planning. So this is things like managing logistics, surveying launch sites, doing trajectory predictions, and other associated tasks that you might do ahead of the actual launch. The third part of this video is going to be the actual mission execution or the actual launch. So we'll talk about the checklist that we went through, some of the procedures that we followed, and overall, how did the actual mission go? And the last and final portion of this, part 4, is going to be looking at the data and results. So naturally, I think after doing all of this work, you'd like to see how did everything turn out. Well, we collected a lot of really interesting data, and we're interested in sharing both the data and some of the techniques we use to analyze that data in this video. So with that being said, like we looked at earlier, it's a large topic, so let's go ahead and jump in and get started. Alright, so to give some context and history, we've got a small science and engineering club going with my daughters and some of their friends, and we're always looking for projects or topics that can be used to get them excited about science and engineering. So we decided that a high altitude balloon, or HAB, would be a great experience for the kids and give them a long-term project to work on. So to start, let's talk a little bit about HAB. So to do this, I'm going to recycle some of the slides that I made for this science club. So first of all, what is a high-altitude balloon? So really, they're really just large balloons that can be used to carry a payload up to an altitude of, I've seen regular occurrences of 115,000 feet. It seems to be pretty reasonable. And really, they're basically a large party balloon. In fact, one high-altitude balloon is usually maybe around 50 normal party balloons, equivalent by volume. Ours turned out to be quite a bit larger. In fact, ours was more like on the order of 100 to 130 party balloons, but that's a topic for a future discussion. So typically what these high-altitude balloons are used for are meteorological surveys. So a lot of people refer to these interchangeably as weather balloons because that is how they're mostly used around the country nowadays. In fact, there are about 900 to 1,300 stations all around the globe which regularly launch weather balloons twice daily to gather these meteorological samples and obtain data about our atmosphere. So the concept of operations for this is actually really simple. So all we're going to do is inflate and then launch a balloon which is attached to a payload, so it can basically just start rising through the atmosphere and gathering data. And obviously as it does this, as the air pressure goes down, as it gets higher, the balloon is going to get bigger and bigger as it rises in altitude. And then while this is happening, the idea is our ground team will hopefully be able to monitor and track the location of the balloon, because as we saw in the previous slide, it's going to go really high and we're going to lose visual contact of this fairly quickly. Eventually, at some altitude, the balloon gets so big that it is just going to naturally burst. And after it bursts, it's going to start tumbling down towards the ground, and eventually a parachute is going to be able to deploy, and the parachute is going to allow the payload box to float gently back to Earth somewhere, and then all we need to do on the ground is basically try to find and recover this balloon and payload. So really, this is nothing more than a larger version of, we're going to have a balloon, we're going to let it go, it's going to go float, it's going to pop, and we're going to hopefully try to pick it up. So that's the game plan of this entire system. Why don't we talk about some of the components that are going to go into making this a reality? So conceptually, this is actually really simple, right? You've just got a big giant balloon, which is going to then carry up a big train of equipment, namely things like a parachute, radar reflector, and most importantly, the payload box, which we're showing in orange. This entire diagram on the left side is what we're going to refer to as the flight vehicle. And as we mentioned, the major component of the flight vehicle is the payload box, which has all of this equipment inside of it and much more. So I like to break all this into sort of 2 major categories. So the first category is things things that we're using to track the balloon during its flight and when it's on the ground. So this includes things like a spot trace unit on an APRS based tracking system, an Apple AirTag, and we are going to talk about all of these in a little greater detail in just a second. So let's defer that discussion for a few minutes. The second major category of equipment is data acquisition and just general science. So this includes things like still cameras, video cameras, data acquisition units, thermocouples, all of this other stuff that is used to actually conduct the science of the mission. So in addition to the payload box, the other thing that is a major component of the flight vehicle is the lift system, right? This includes things like the balloon and the helium. We're going to see later that you actually have to have specific types of lines connecting all of them. So the lines that you connect anything together with have to be able to break under 50 pounds or less of tensile load. We also have things like we mentioned, like a radar reflector to help the entire flight vehicle visibility from the perspective of other potential aviation traffic. And obviously we have a parachute to help recover the payload box after the balloon bursts, and it will slow the descent of the entire flight vehicle as it comes back down to Earth. And then lastly, one thing that is not pictured here in this flight vehicle, but is also another critical piece of hardware and software that I think warrants discussion real quick, is things like for our ground station. So obviously, if we're going to be tracking this vehicle as it's flying around, we need to be tracking it from the ground. We can't follow it around in the air, so we need to set up a ground station that would be able to receive things like our broadcasted packets, as well as other types of signals, so we can monitor the progress of the actual entire flight vehicle. So we'll talk all about these in just a little bit. So in a nutshell, this is what the flight vehicle looks like. And as I mentioned, I think it warrants a little bit further discussion about the tracking system. So let's talk about the three major tracking systems that we're using on our aircraft. So the reason we need these tracking systems is that after we launch the balloon, I've seen cases where these balloons can float for, potentially hundreds of miles away from the launch location, and we need to be able to monitor where it is so we can follow it and track it in flight, and therefore it's going to give us a much better chance of successful recovery if we're able to monitor its progress. So again, in the name of aerospace redundancy, we are going to use multiple tracking systems to make sure that if one of them fails, we still have two or potentially three other systems as backups. So let's talk about the systems we're using. We're using three. The first is probably the simplest, and this is just a simple Apple AirTag. And again, the idea with this is that if you have some kind of Apple device, right, like an iPhone or an iPad or what have you, right, these things can talk with GPS satellites, right? This is how your phone knows where you're located. So in other words, the phone knows where it is located. Now, the way an AirTag works is if an Apple device happens to walk by or be in close proximity to one of these Apple AirTags, it can talk to the Apple AirTag, and the Apple AirTag can talk to it, right? So basically, the AirTag and the phone are able to talk, and since the phone has the information about its location, and the phone can also connect to cell towers that may be nearby, you can basically transmit the location of where you saw that AirTag to the cell tower, which can then forward it on to Apple servers, which are then networked to other computers, right, which we refer to as the cloud. And again, I apologize if this is a simplified diagram. Remember, we were using these slides to kind of explain to some of the kids in the science club. And now, once we have that information up in the cloud, we can send that to our ground station laptop using whichever method we want. As long as that laptop is connected to the internet through either a Wi-Fi hotspot or a cell phone hotspot, we should be able to get the information to the AirTag, right? So this is one system that we could potentially use to track the location of the payload box. Now, obviously, the problem with this is that it only works if an Apple device happens to go in close proximity to this Apple AirTag. So in other words, this is only going to work once the payload box lands on the ground, and hopefully it lands in some area where somebody with an Apple device might walk by it. So again, This is not going to be great for real live telemetry. It's only going to be helpful as a kind of a backup system in case something goes wrong and this thing lands in some farmer's field and a farmer happens to walk by it with an iPhone in their pocket. So not a great system, but it's really cheap. I think this AirTag was only like $35 or something like that, and it's incredibly light, right? It's just that little AirTag, which again weighs a few grams. So it's light, it's cheap, but it is not very suitable or robust for our application. So this brings us on to our second system. All right, so our second tracking system is a commercially available off-the-shelf unit known as a spot trace. So what this spot trace unit looks like is right here. It's this little black thing. It's about the size of half of a deck of cards. And what this spot trace unit does is, again, it has a GPS antenna / receiver on board. So it can gain talk to GPS satellites, and basically it can know its own location, right? It can compute its lat long by receiving GPS satellites. So again, it knows where it is pretty much anywhere in the world, right? As long as it is facing skyward, and we're going to talk about this a little bit later, it should be able to talk to GPS satellites and know where it is located, right? So that's great. Now we also need to get that information though off of the spot trace units and back into our hands. So this is where this is a much more robust and better system, because this spot trace unit, in addition to talking to GPS satellites, which we're kind of illustrating here in blue, the Spot Trace company basically has a contract, I believe, with Globestar satellites so that they can talk back and forth between the Spot Trace unit and the Globestar satellites, which again I'm denoting here in red. So basically what happens is that this Spot Trace unit can compute its own position anywhere in the world and communicate with overhead satellites anywhere in the world to send that location information up to the Globestar satellites, right? So once that happens, right, these Globestar satellites have a uplink and downlink somewhere. I don't know how they've got this sorted out, but long story short, they can get that information from the Spot Trace unit up to the satellites and then back down to the ground, which can then be forwarded again off to the cloud, which then can be sent off to us and our laptop. So again, it's a little bit of a convoluted path, but this definitely works. And again, the benefit of this, right, is as you can see, it does not require anybody to walk near this spot trace unit. And in fact, this spot trace unit theoretically should be able to report its own location anywhere in the world. So even if you're outside of range of cell towers or any users, if it was dropped in the middle of the Antarctic, theoretically this would still work and we would know where this spot trace unit is located, right? So as long as it's on board and as long as it's pointing skyward, we should be able to find its location pretty much anywhere in the world. So that's the benefit. The drawbacks of this unit is it's much heavier than an Apple AirTag, and you actually have to pay a monthly subscription fee for this service. So again, I've got a dedicated video talking about the spot trace and the subscription, but for this purpose, it actually is quite attractive. All right, so our third tracking system is what's known as an APRS packet system, or an automatic packet reporting system. So the way this works, it's a little bit of a homebrew solution in the sense that if you go ahead and buy yourself a GPS receiver, again, what this GPS receiver does, obviously, is it's hooked up to a GPS antenna, and it can then receive GPS satellite signal information, and again, it can compute its own position, right? So this little chip will know where it's located, again, anywhere in the world, and it doesn't require any other information, doesn't require any other users, right? It can compute its own location. Now, we need to get that information off the unit, so we are going to hook it up to an Arduino so we can talk to that GPS receiver, we can query the information, and then we can send that information via the Arduino to a radio. So we are going to use it's known as a HX1, and it operates at the frequency you see listed there, 144.39 megahertz, which is sort of the VHF band. And what we can do then is we can broadcast that information out to anybody that's listening via an antenna, right? So all of this unit that I've got boxed up here makes up what we are calling the APRS tracking system. So all of this, again, is about the size of a deck of cards, and it really doesn't weigh a whole lot. You can see it's a bunch of just things like an Arduino, a GPS receiver, a very small antenna, a very small radio, and that antenna is a little bit bulky, but it doesn't weigh a ton. Long story short, we can jam all of this into our payload box, and we now have the ability to broadcast out the position of the payload box, or that GPS receiver more specifically, and anybody that's listening can pick up that information. So hopefully what we're going to do is we're going to have a ground antenna that can hear the broadcast made by the air antenna. We're going to hook that up to basically a ham radio. We're going to then hook up that ham radio to our laptop, and what we can now do with this system is basically track the location of that GPS receiver, which is inside the payload box, in real time during the mission. And again, what's nice about this system is, as you can see, we're not really depending on things like Globestar satellites or anybody else's network other than the GPS satellites, and that's pretty rock solid, right? That's not going down anytime soon. So this is a very self-contained system. We don't actually have to pay a subscription fee for this or anything like this, and it's a great opportunity for the kids to learn a little bit of programming and putting some electronics together. So this is our third system, our APRS tracking system. And again, we've got other videos talking about this in more detail if you're interested. So those are our three main tracking systems. All right, so with that discussion out of the way, I think what might be interesting is let's just go ahead and take a look at the overall completed payload box. And as you're going to see, there's going to be a lot more components than just the tracking systems, right? We've got all those data acquisition and other science equipment on board, but I think it would be interesting to see everything in one box. So let's jump outside and I'll show you what the entire system looks like. All right, so we did a lot of work. The kids put a lot of effort into this, and I think we've got the payload box pretty much all ready to go. So I figured what we might do is just walk through some of the subsystems just to show you what we're carrying on board. So let's take a look. So as you can see, obviously we encased everything inside a pretty thick styrofoam cooler and painted it bright orange for high visibility. One of the main payloads we've got here, as you can kind of see it through this acrylic dome, is our 360 camera. So this is an Insta360 1X camera. It's kind of an older 360 camera, but again, that's probably good in case we end up losing it. So we first tried to enclose the 360 camera. It comes, you can buy a specific dive case for underwater footage for that camera, and we thought that would be great for protecting it, but the problem was that you don't have access to the USB charging port when you put it inside an underwater proof camera. So instead what we decided to do is just poke the camera out through the payload box, and then we just bought this really simple acrylic dome to kind of protect it. So we're going to give this a shot. I think it kind of looks neat. So that's one of the items on the exterior you can see. On this side of the exterior, you can see we actually have a basically a temperature sensor, kind of a thermocouple that is sticking out to get exterior temperature. And we actually have two of those. So we have one on this side and then one on the opposite side as well. So in the name of aerospace redundancy, we're actually going to collect that signal using two separate, completely independent sensors and data acquisition systems. Again, for redundancy. What else is here on the exterior? If we flip this box around, I can show you on the far back. We also have a pretty standard passive piezoelectric buzzer. So this is hooked up to one of our systems where this is going to just buzz and make kind of an annoying sound under 10,000 feet, just so you can hear it and hopefully help with retrieving it. We also put a nice little warning or little instruction out here that in case some farmer finds this and this thing is buzzing and is being super annoying, we just told them just cut this black wire if you want to shut this thing up. But again, that should hopefully help. What else is on the exterior? As you can kind of see, we also slapped on a lot of notices on, hey, this is not a explosive device or anything like that. It is just an elementary school science experiment, and we put some contact information so that hopefully if somebody does find it and our tracking systems fail, they can get in touch with us and we can retrieve the payload. So that should hopefully be helpful. Let's move up here to the top of the box. Let me swing this around. we've got our two GPS antennas here. So again, once again, redundancy is the name of the game here. So we have multiple ways of trying to track this. So we have two GPS systems, and I'll talk a little bit more about what those two systems are, but both of our antennas are outside and they are above. You can kind of see the ground plane for our antenna. So these four wires that are sticking out are the ground plane for our antenna. The main element of the antenna is, I don't know if you can see this down below, but we have this poking out underneath the bottom. So this is a ground plane, or excuse me, this is the main element of our antenna. That antenna, again, is tuned to the APRS frequency. I have a completely separate video talking about how we ended up tuning that and making sure that it was resonant at the appropriate frequency for APRS packet transmission. But that's the game plan. Yeah, and then obviously the kids signed the top of the box for fun. Let's take a look inside. So if I take off this lid, I'll show you one of the kind of interesting components. And in fact, let me take off these antennas so that these antennas aren't kind of in the way. All right, so here's the lid, okay? And you can see right here what we've actually got. This is a commercially available off-the-shelf spot trace unit. So again, I've got a separate video on this, but this is our satellite-based tracking system. So this should talk directly with basically global satellites to not only get GPS position, but also to transmit its position. So we should be able to find this unit pretty much anywhere in the world. So even if we're out of cell signal, if we're out of APRS range, we should be able to hopefully find the unit via this system. Now, one caveat with this spot trace unit is that it has to be facing up. So this top plane of the sensor is supposed to be pointed toward the sky in order to get good reception. So one thing we were worried about is, what if this payload box lands and tips over on the side or even upside down? It lands on a hill and starts rolling down or something like that. So to mitigate that, what we did is we 3D printed this is our poor man's gimbal system. So you can see all this is doing, right, is it is suspending the spot trace unit on a kind of flexible little twist tie system. So basically, if the payload box lands straight up and down in the nominal configuration, it's no problem. The spot trace unit is in the proper orientation. If it lands on its side, right, gravity is just going to allow this thing to drag the spot trace and still keep it in the proper orientation. And we sized this thing so even in a worst case scenario like this, the payload box falls completely upside down, you can see that the spot trace unit is still pretty reasonably pointed upwards. And if you look inside, you'll see that we left a fair bit of area of free space right here, so the spot trace has room to swing around in the event of a off nominal landing. So that's one of our tracking systems. While we're talking about tracking systems, let's take a look inside here and we'll show you some of the other components that we put in here. So over here in this blue box, this is our APRS based tracking system. And again, I have a completely separate dedicated video talking about what we did and how we built this APRS based tracking system. So again, the idea with this is that it is going to use one of the GPS antennas that we showed on the top of the box, and it's going to know its position, and then it is going to broadcast that position out via an APRS packet using an HX1 radio transmitter system. That system is hooked up to our little homebrewed antenna, which you can kind of see here. The antenna's got, this is our little 3D printed antenna holder to get it in the proper configuration. So the antenna and the blue box sort of all go together, and that's one of our major tracking systems. So this should allow us to get real live update positions reports of the payload box every 15 seconds during the mission. So that should hopefully be pretty helpful for tracking the unit in flight. So again, this is also going to transmit not just the position and altitude, but also the temperature of one of these exterior thermocouples, and also we have an interior temperature sensor as well, just so we can see the interesting difference between the interior and exterior temperature. One reason why we're talking about temperature, what I will mention is if you look at the styrofoam box, actually here, scoot over here a little bit so we can see the out of the shade. There we go. So you can see this is a pretty thick box. So we're hoping that this insulation is going to help with the with making the inside and keeping the electronics warm during the flight. Well, we've tested this, and just by virtue of the number of electronics running in here, it stays somewhat warm at ground temperatures. We tested this kind of in the cooler winter days, and you can definitely notice a difference in the thermal gradient between the interior and the exterior. To help further with that, what we're going to do is we are actually going to also throw in a few of these, pocket hand warmers. So these are pretty darn light chemical-based systems that are just going to radiate heat for hopefully the duration of the mission. And we actually, if you come in here and look, one of the main critical components that we're trying to keep warm are these batteries here. And as you know, lithium polymer batteries do not do well in the cold. So we actually built a battery stand. I don't know if you can see these. There's this blue 3D printed layout configuration. This holds the batteries up a little bit, and there's room underneath for us to slip one of these hand warmers underneath. So hopefully this hand warmer is going to warm up. The heat is going to radiate up through the batteries and warm up the entire system, the entire interior of the payload box. And most importantly, it will keep the batteries warm. Now, while we're looking at the batteries, maybe what I will mention is if you look at this, we've got a ton of batteries here. And this is probably one thing that we might want to try to improve in the future is that we've got four. So we have 3 of these USB standard power bank batteries. One of them, this guy powers the 360 camera. The other one in the middle powers our GPS tracking unit, which we're going to talk about in a second. And the third one over here powers our Canon S100 still camera. This LiPo battery is a 2-cell 1300 milliamp hour battery, which is going to power our APRS based tracking system. So again, the power management probably could have been done better. We ran into issues where we were trying to run multiple USB sources off a single larger USB battery, and we ran into kind of current draw issues. So that's one reason we decided to go with this redundant independent battery system. So literally one battery per system. Again, that helps with redundancy, and it also helps us with the current draw issue. So again, that's all of the batteries. So let's keep talking about some of these systems. So we obviously talked about the 360 camera you see here. We talked about the APRS-based tracking unit. Let's go over here to this orange box. So this orange box over here, let me see if I can spin this a little bit. Maybe we can get the sun to shine on it so you can see this a little bit more easily. So the orange-based system is our high data rate position logging system. So this one is a completely separate redundant tracking system, which has obviously a GPS antenna hooked up to it, and it is hooked up to our 2 thermocouples, one of the external ones and another completely separate independent internal one. So all this guy is in charge of doing is logging the position, namely the latitude, longitude, altitude, as well as other interesting GPS information like the number of satellites visible, HDOP, and also logging all of the those 2 temperature sensor measurements. It's just going to do this at a much higher data rate, and it's going to store all that information on board on a micro SD card. So this orange box is completely separate than the blue box, right? So the blue box is going to transmit that information hopefully back to us in real time, but at a slow data rate. The orange box is going to be logging basically the same information on a completely separate independent set of sensors and batteries, but at a higher data rate. So that's the game plan. And again, we've got a completely separate dedicated video on the orange GPS logging system if you're interested. Okay, so let's see. The last system I think we need to talk about is over, let me spin the box a little bit so again we can get the sun here, is over here you can see we've got an old school point and shoot Canon S100 still camera. So what this is going to do is we have it running custom firmware. So we have CHDK running on it, which stands for, what is that? That's the Canon Hackers Development Kit. Basically, it allows us to hijack the firmware on that Canon camera and let us basically program special customized functionality. So in our particular case, what we did is we loaded a time-lapse program onto it. So it will shoot a still photo every 45 seconds. And we have this Canon camera powered externally by one of these larger capacity USB batteries. So we've tested it, and hopefully this should give us a fair amount of photos, still photos, as we're ascending and descending. So that's the game plan. And I think with that being said, that is pretty much the entire payload box that we've got in here. So yeah, in addition to the payload box, I think the only other two things that the balloon is going to be in charge of picking up is we're going to fly a radar reflector that's going to help hopefully with visibility for any external traffic or basically radar stations that might be able to pick it up, and obviously the parachute that is going to have to be hoisted up with this entire configuration. So with that being said, I think that is the entire payload box that we've put together. So again, the kids did a great job working on this over the past 6 months, and I think it is now flight worthy and it's ready to go. So why don't we go ahead and see if we can get this set up. All right, so now let's go ahead and move into the mission planning phase of the discussion. So I'd like to cover a couple of topics in this section. Namely, let's talk a little bit about some of the laws and regulations, and then we'll go into some of the ground testing that we performed. And we actually included and performed a full mock flight test. And then let's also cover how we did some of our trajectory prediction as well as site selection. In terms of laws and regulations, you can find some verbiage in the Code of Federal Regulations here. Now, first thing I should mention is I'm obviously not a lawyer, so you shouldn't really take my word for it and do your own research. And if you do, you'll find several sources that distill some of the relevant rules and regulations down to a few key points. So, namely, there are FAA rules and FCC rules that you need to abide by. So this first item here is definitely an FCC rule, right? Everyone's been on an airplane before. You know that you need to turn off your cellular devices when you're in the air. So you can't just simply throw a cell phone in your payload box and use that to track your balloon. So this is what drove the design of our tracking systems. You notice that we don't have any cellular devices on board. Number two says that the payload can't exceed a weight to size ratio of 3 ounces per square inch. They really mean a weight to surface area ratio here. So what you need to do is make sure your payload box is somewhat bulky and has a large surface area, and you should be fine. So again, this is trying to avoid the situation where people might have a really small, dense payload box, which could be a potential hazard when it's coming down through the atmosphere. So, number three, your payload box can't be more than 6 pounds in weight, right? Now, 4 is interesting as it kind of relates to the previous rule, is if you have a lot of payload, you're actually allowed to spread that out over multiple payload boxes as long as each one of those individual payload boxes meet numbers 2 and 3. You can have multiple boxes, but number 4 says that as long as you have all of your payload boxes together, can't be more than 12 pounds in weight, right? Number 5 relates to all of the ropes or string that you're using to build up your payload train. So each one of these ropes or strings needs to be able to be broken with less than 50 pounds of force. So you should probably be using fishing line or monofilament. Don't be using heavy duty rope. Number 6 is pretty obvious and hopefully kind of a duh rule, right? Just don't be a hazard with your balloon to people or property, either on the ground or in the air. And number 7 is don't drop anything from your payload balloon when it's at altitude. So again, if you go to several other sources, you'll see that they pretty much agree on these set of rules, and this is a set of regulations that the community has converged to and that we are going to abide by. So all of our systems meet all of these rules and regulations, and we'll show that later. This should make it so we are ready to go and in compliance. So this brings us to ground testing. For those of you who have flight test experience, you know that you spend orders of magnitude more time on the ground testing and preparing than you do actually flying, and for this project it was really no different. Over the course of about 6 months, we had approximately 15 science club meetings. Most of them were actually outdoors in our garage due to the pandemic. And the majority of these meetings were spent building and testing the various components of the flight vehicle. We did extensive ground testing, which included things like taking the entire flight vehicle to the park and walking it around to gather data sets and ensure that the communication links were working. We even did a couple of rounds of ultimate hide and seek where we split the kids into 2 teams, and the first team was in charge of hiding the payload box somewhere in our city, and then the other team had to track and recover the payload. Most of our ground tests were focused on the APRS based tracker and the Arduino data logging system, but we also tested our camera, both the still Canon S100 and the video camera. We even did some cold soak tests where we placed all the relevant electronics inside the freezer and verified that they were able to withstand the low temperatures and still function properly. Granted, we expect the outside air temperature at altitude to be significantly lower than the freezer, but we're hoping by the time we add the chemical heaters and the styrofoam insulation, the interior of the payload box will be closer to these freezer conditions. One of the most important parts of mission planning is developing a procedure for the inflation and release of the balloon. Now, what makes this complicated is the fact that there are so many moving parts and people involved that it's easy to make a mistake and potentially lose or damage the balloon. And given that it takes a significant amount of helium, and helium right now is not cheap, it is important to practice this and get it right so everyone knows their job. And here's the process that we settled on. So the most important thing to do is to just lay out all of your components and have them ready at hand before you even start the process. So some of the key components right now are obviously the helium tank, and then attached to the helium tank you're going to need a regulator, and then attached to the regulator is a long vinyl tube, which we're referring to as the inflation hose. Now at the end of the vinyl tube that interfaces to the balloon neck, we actually ended up 3D printing a adapter part to make sure that the diameters meshed nicely, and then that we wouldn't have any issue putting the neck on and off of the inflation hose. Then we have the uninflated balloon. This is obviously the most important piece of the entire operation, and we want to lay that down on a nice, smooth, clean tarp. So you don't want to lay it directly onto the ground where you have the risk of some sharp object poking it or prodding it or damaging it. So you want this tarp down for protection. Another piece of equipment that's important is some sort of anchor that you can tie the balloon to while you're making final preparation. So in our case, we used a concrete anchor, which really was just a PVC pipe filled with sand and rocks. Lastly, we also have a weight, or a set of weights, which really were just a couple of milk jugs or water bottles filled with the appropriate amount of water. So the key here is that this weight, it is filled with the amount of material so that the entire system weighs the same amount as the payload box plus the amount of positive lift that you want the balloon to have. So the idea is when we fully inflate the balloon, we can quickly test to make sure that the balloon has enough net lift so that we attach this weight to it and the balloon should be perfectly neutrally buoyant. So this was the game plan of placing all of the equipment out in the field ready for use. So now we're ready to start the inflation process. Alright, so this is where all the kids came into play and where it's actually very helpful to have a lot of free helpers to assist with the inflation process. So we actually assigned a fair number of specific designated jobs to some of the participants. So one, we had someone that was dedicated. Their only job in life was to operate the helium tank, basically just turn on the helium on or off. We also had someone known as the balloon neck technician. So their main primary job was to manipulate the neck of the balloon and put it on and off of the inflation hose at appropriate times. We then had some balloon holders. That are these people here. You can kind of see them denoted. And their job was really simple. It was really just to hold the uninflated balloon up above the tarp. So they were all wearing latex gloves so we didn't risk getting any body oils onto the thin skin of the latex balloon. It's apparently fine to hold the neck of the balloon with bare hands because the neck of the balloon has significantly thicker latex and rubber, so you don't really have to worry about it causing any chemical reactions or freezing human oil up at altitude. So this is okay to hold down here, but all these balloon holders that were holding the thin part of the main balloon were wearing gloves. We also had someone known as the balloon safety holder, and these, you hear those jokes about those people like, you got one job, right? This person's one job was to hold onto the neck of the balloon and not let it go until it was appropriately the right time. So their one job was to hold the balloon and be the last line of safety. We also had someone known as the weight technician. So they were in charge of holding these weights. Remember we talked about these pre-allocated and pre-weighed weights? And they would attach it to the balloon at the various times when we were testing to make sure that the balloon was providing enough lift. And finally, we had a payload technician. So their job was to get the payload box ready to go, making sure that it was ready to collect data or perform whatever mission was necessary, and it was ready to get attached to the balloon at the appropriate time. So the first step in this process, after we laid everything out, was to arrange everyone in this orientation, right? So the helium tank operator is situated near the tank, ready to turn the valve on and off. And then we had all of these people, like the balloon holders, the balloon safety holder, and the balloon neck technician, were all crowded around the balloon, and they were holding it up uninflated above the tarp and basically ready to go. So all we need to do now is have the helium tank operator start the flow of helium. So they crack open that valve and they start letting helium flow, and the balloon is going to start slowly inflating. During this time, the balloon holders are basically just repositioning themselves and making sure that the balloon is inflating nicely and smoothly and is not bumping into anything sharp, right? After this, the next step in the process is to simply go ahead and continue inflating the balloon, and basically the balloon holders, their job now transitions from holding the balloon to basically steadying the balloon. One of the things you got to worry about, especially when you're out in the field in a potentially windy environment, is as this balloon gets larger and larger and starts floating, the wind has a chance to pick it up and move it around. And again, you don't want this thing bumping into anything sharp. So the balloon holders are gathered and situated around the balloon and are able to hold it in place as it's inflating and starting to lift off. Okay, so at some point, the balloon is going to get large enough where we need to test to see if it has the proper amount of positive lift to pick up the payload box and ascend at the desired rate. So what we have is the helium operator will stop the flow of helium, and the balloon technician will be in charge of removing the neck of the balloon from the adapter and just putting the inflation hose on the floor. So at this point, this is one of the most dangerous points because the balloon is effectively almost free at this point. So again, remember, this balloon safety holder, they need to be just holding onto that neck for dear life and making sure that it doesn't leave, and also pinching the neck to make sure that helium is not escaping out of the balloon. Okay, so now what we can do is we can have the balloon neck technician go ahead and tie the neck closed. So when they tie it closed, we actually include a little loop of paracord around that, so there's an easy attachment point for various items. So one of the items that you're going to want to attach right now is what we're calling a safety leash. So again, this was just another piece of paracord hooked up to a quick release carabiner that we could just snap on and off of this loop and attach it to the concrete anchor. So now this is a little bit more safe because the balloon is now safely attached to the concrete anchor and shouldn't be able to basically just float away. So now that the balloon is safe on the leash, we are going to attach what we're calling a primary loop, which again was just another loop of paracord. And the idea is this primary loop is going to hold our payload train and anything else that we want to attach to it that is actually going to fly. So the balloon neck technician can simply attach that loop to the balloon, and we're ready for our next step. And what we're going to do now is get ready to test the amount of lift that the balloon is able to produce. So to do that, we have the weight technician come in and attach the water bottles, which are weighed to the appropriate amount, to this primary loop. Everyone else can now sort of step away, and these balloon holders can just make sure that wind doesn't, again, blow the balloon in any undesired direction. So once the weight technician has the weight attached to the primary loop, we're ready for our start. This is kind of the first moment of truth, right? At this point, what we can do is have everybody basically let go of the balloon, take one step back, but be ready to grab the balloon if anything goes wrong. If it either goes up or down in a fashion that we don't like, we can quickly step back in. The idea, all we're trying to do at this point is let the balloon float free, and ideally, if we have inflated this with the right amount of helium and we weighed the weight properly, what should happen now is the balloon should just be neutrally buoyant. It should just float there in midair, right? That's what we're going for. If that's the case, that means we have the right amount of helium and we can go ahead and start thinking about actually flying our real payload. So to do that, what we're now going to do is have the balloon safety holder come back and grab the neck of the balloon, and the weight technician can then unclip the weight from the primary loop. So now the balloon is trying to fly away, but we've got both the balloon safety holder and the safety leash attached to it. And what we can do now is have the payload technician come in and attach the payload train to the primary loop. So that's what this cyan line is, coming from the primary loop to the payload. Now, One of the other things that are interesting is the case that we were going to use, and actually we're going to show this later as this is a good thing to do, is we actually also attached the payload down to the concrete anchor. So this was effectively another safety leash. And the reason we're going to do this is so that we can do sort of a soft launch, in the sense that we can let the balloon start to ascend while it's still attached to this longer leash here, which is this sort of cyan line. Once we verify that the ascent rate of the balloon is appropriate, we can then pull it back down. So all we're doing here is, instead of having a free balloon, we're creating a tethered balloon at this point, because we're really not quite ready to let this thing fly free. We still want this thing to be able to be pulled and reeled back in a little bit. So now that this is all attached, we're pretty much good to go, and what we can think about doing is disconnecting this safety leash, the red safety leash, and now the balloon, yeah, it's almost ready to go, although it is still attached to our concrete anchor via this cyan line. So now what we can do is we can go ahead, have everybody step aside, and then slowly release the balloon. We can reel it up, and basically it's going to start ascending. It's going to pull up the payload, and it's going to pull up this secondary kind of leash line. And again, it's going to be clear what this is for in a little bit when we actually do the real launch. And in fact, we're going to use this procedure when we actually do what we're calling our mock flight test. This mock flight test was actually a community event where all the kids at all of the local elementary schools decorated white paper bags, and then the bags were lined up along the main street of our town with small LEDs inside. So it was supposed to be an inspirational community building event, and my wife is actually one of the main organizers for this, and as such, when they were starting to brainstorm new ideas for this year's event, we threw out the idea of using a weather balloon to hoist an LED lighting array into the sky to draw attention to the event. This actually gave us a great opportunity to test our inflation procedure as well as test some of the payload equipment. We basically got to do a full dress rehearsal of the launch. The only difference was that in this case, the balloon was designed to be tethered to the ground and only fly about 80 feet in the air. And in this case, what we did is we mounted an array of color-changing LEDs to the top of the payload box so they would shine up onto the balloon and illuminate it and give it the appearance of a glowing orb in the sky. And here's the final result, and I'd say it worked out pretty well. Aside from the fun artistic experience, though, this gave us a chance to really exercise a large portion of our process and checklist, and it gave the kids some great experience with the workflow, and it allowed us to work out some of the bugs and refine our process, which is going to help a lot when we do the real launch in the near future. Alright, so with the flight vehicle pretty much complete and all of our preparations in order, we're basically ready to start making some predictions about the trajectory of the balloon. So to do that, we needed to gather some key information like what we felt the payload was going to weigh. Now again, this is going to be the payload box, the radar reflector, the parachute, the lines, all that kind of stuff. And as you can see, we come in here at about 2,300 grams or a little over 5 pounds. So again, we're underneath that 6-pound limit, so this should be good. We are using a 600-gram latex balloon, so that's the weight of the balloon, and what we would like is we would like to have about 3/4 of a kilogram of positive lift, so this will get us a pretty healthy ascent rate, and it's therefore not going to take all day for the balloon to reach altitude and burst. So what we can do now is, armed with these first 3 numbers, what we can do is actually run over to a website, and I'll pull that website up right here just to show you. So there's a great website called highaltitudescience.com. They have a lot of information about weather balloons, and one of the tools that they provide is this balloon performance calculator. So you basically put in all of this information, like the balloon size in terms of how much the balloon, the empty balloon weighs, how much your payload weighs, what your positive lift is, and you go ahead and calculate it. And the nice thing about this is that it will tell you how many cubic feet of helium you're expected to need, and other performance numbers, such as, for example, when they expect the balloon to burst, how long it's going to take, and the ascent rate. So all that information is we captured it here in this table. So this is pretty much our estimated mission profile for our system. So just to read off a couple of these numbers, we anticipate, around an 81,000 foot burst, and we're going to see that this is surprisingly accurate when we go look at the actual mission that we executed. It's going to go up at about 4 meters per second. and take a little over an hour and a half to get to a bursting altitude. Now, given the parachute that we're using, we also were able to estimate a descent rate. So based on the manufacturer's estimated, the parachute manufacturer's, that is, estimated parameters, we estimate it's going to fall at about this speed and take over an hour to fall down from burst altitude. So this is what our total mission time is going to be from launch to recovery, is, you know, a significant non-trivial amount of time. You know, we're talking almost 3 hours here. So just for comparison's sake, just to give a little bit of context, you know, here in Seattle, the Space Needle is our local landmark at about 650 feet. Mount Rainier is the tallest mountain in our state at, you know, about 14,500. Mount Everest here is about 29,000. Commercial airliners cruise at, you know, at a flight level about 36,000 feet, and we're anticipating our weather balloon, which the kids designated and called the Space Shrimp, to burst at 81,000 feet, so significantly higher than an airliner. Of course, we're nowhere near to space. I mean, I think you see a lot of these people talk about launching your balloon to space, but really you are nowhere near the Kármán line with any of these high altitude balloons, at least these personal kind of for fun hobbyist balloons, right? The Kármán line is way up at 100 kilometers, or, you know, 328,000 feet, so nowhere near there. And just for fun, we showed the kids that, you know, the International Space Station is way up here. So again, we're higher than a airliner, but not out to the edge of space by any means. Definitely in the upper atmosphere, but you know, not to space. So what we can now do with this information and all of these mission parameters, now that we know how fast the balloon is going to go up, where it's going to burst, and all of that kind of stuff, we actually want to start thinking about running some trajectory predictions so we know where is the balloon going to go and where might we expect it to drift. So to run these trajectory predictions, let me point you to this website here. So this is a really great website which will actually allow you to input all sorts of information, most importantly where you are going to launch from, and then things like when you're going to launch, as well as all of these parameters that we just talked about, things like your ascent rate, how high it's going to burst at, all of that kind of stuff. So for example, for giggles, I don't know, let's just go ahead and set this with the map and I'll show you. I don't know, let's say we go, I don't know, somewhere around here, right? Let's say you're going to launch from here, and let's just use some of these default numbers. Later on, when we actually are running analysis for our particular mission, we'll go ahead and use the proper numbers, but for now, I'll just show you that if you run this, it will show you, given the current weather forecast on this particular day, it's anticipated that the balloon is going to fly and rise and then burst here and then come down and land somewhere over here. So again, this is really fun and helpful, as you can go ahead and do all sorts of different Monte Carlo analysis by varying some of these different parameters, varying the launch locations, varying the launch time, all of that kind of stuff. And then you can actually even save this to a CSV file up here. And then if you do this and run enough trajectory predictions over a wide enough range of times and parameters, you can get a reasonable idea of where the balloon is going to go given a certain launch site. So that's probably the next thing we want to talk about, is now that we have this tool and we have the inputs that are needed to go into the tool, we also need to think about where are we going to launch. So let's talk about that next. So after playing around with the trajectory predictor a little bit, we determined that we probably needed to find a launch location that was on the east side of Washington State. So we're over here in the Seattle area, and for those of you who have been around Seattle, you know that you can see from this map, there's a lot of water, and in fact there's a lot of trees and forests. In fact, I think we're nicknamed the Evergreen State because of all of these national forests and trees around here. Long story short, while this is beautiful for hiking, if you have a balloon come down in one of these forests, there's probably no way you're ever going to be able to recover it because it's going to be lost in the woods. There's probably no roads to access it. So we don't want to find launch sites over here on the western side of the state. So we're actually, in fact, going to need to come all the way to the eastern side of the states on the other side of the mountains, because the terrain is a lot more flat and open, sort of farmland, and that's going to make recovery a lot easier. So after a bit of research and, like we said, playing with the trajectory predictor, we came up with about 3 separate sites. Whoops, sorry, this is site number 3. Let's go back to site number 1 and we'll walk through these in order. So the first site that we found that was closest to Seattle was basically this was a school administrative and elementary school kind of facility all located in one area. One thing that we were obviously looking for was an area that had some wide open fields that we would be able to do our launch in, as well as, you know, be reasonably accessible from the road so that all of the participants could drive and park fairly close to the launch site. So here was one location, and again, these people were great. We called the school district, we told them what we were wanting to do, and we asked for permission to use the fields after hours on the weekends, and they said that was no problem. So this was our first location, and it was about a 100-mile drive, or, you know, about an hour 45 minutes away from Seattle. So we did have to go quite a ways for this. Our second potential site was right along the river, the Columbia River. So this was basically a public beach. It had a boat launch, and again, it had some nice open areas that we would be able to use, but it was a little bit further away. So now we're talking about driving over 2 hours to get to the launch site. And then finally, our number 3 potential launch site was another elementary school, which was even farther, now about 150 miles away from Seattle, or a 2.5-hour drive. And again, this was an elementary school. We called them and obtained permission, and they said that would be no problem. And we were excited to potentially use this site. So let me just show you where these 3 are sort of in relationship to one another. So here's the first location, here's the second location, here's the third location. And again, if you zoom out, you can kind of see that they are all in sort of central and eastern Washington. And the reason we chose these 3 sites were because A, of the accessibility we talked about, and then also, more importantly, we ran several trajectory predictions at all 3 of these sites, and all of them had favorable landing locations. Now, the question about which one we were actually going to go with on launch day came down to running trajectory predictions much closer to the actual launch window. What I mean by that is, if you come back to this launch trajectory predictor, as you can probably imagine, this heavily relies on wind forecasts, right? Depending on the weather, this balloon can go anywhere. I've seen it actually in some of these locations go all the way up into Canada, depending on what day you launch. And furthermore, you can only pick a launch date that is, I think it was, several days in advance, but it's not months, right? Because you obviously can't make weather predictions months in advance. So you have to run these trajectory predictions continuously, and then we actually had to make a game day decision of, we ran the trajectory prediction the morning of, and then saw where it was going to land, and then chose a launch site, either 1, 2, or 3, based on which was going to give us the most favorable locations. So what might be interesting is, let me show you some of the Monte Carlo analysis that we did, where we basically varied all these parameters, saved them as CSV files, and then plotted them all just to get a rough idea of where it was going to go if we chose any one of these 3 launch locations. Alright, so to do the Monte Carlo trajectory analysis, we basically ran and set up an entire run matrix where we looked at all of the different launch locations, and then we looked at varying parameters such as the ascent rate, the burst altitude, and the descent rate. We decided that we were just going to fix the launch time and date to be sort of a nominal time. Because as you can probably imagine, if you start thinking about varying the launch times as well, this matrix starts blowing up exponentially. So we decided this is probably enough. So we chose to launch around 11 a.m. local time, given the time it would take us to drive out, set up, get the balloon in the air. We thought this was pretty reasonable. And we basically ran all of these different predictions in the calculator, saved them as CSV files, and then wrote a little bit of a MATLAB script to analyze them. So let me go ahead and run this, and I'll show you some of our predictions that were made several days in advance. Let me go ahead and, sorry, this pulled up on another screen. Where did it go? It is down here. Here we go. Let me pull this up and I'll show you. So here are all of the predictions from our 3 launch sites. So you can see here's launch site number 1, launch site number 2, launch site number 3. And as you can see, pretty much all of them drift to the northeast, but there's a significant amount of variability depending on these parameters. So all we were trying to do was get a reasonable idea of the probability distribution of the landing locations. And we looked at these and we said, all of these look pretty reasonable. I mean, some of these ended up going pretty darn far north, so we're going to hope we don't end up in these situations, but otherwise, all of these land in a fairly wide open, flat, set of terrain where recovery should be doable. So, given that fact, we said, okay, these predictions were done several days in advance. So what we instead decided to do was just continue watching the weather, and then we actually did another set of predictions the morning before we went out and launched. So let me load those up, and I'll show you what those look like. All right, so here's the data set that we ran just a few hours before, and as you can see, it changed somewhat significantly. Namely, our launch site number 1, we noticed that the winds or the weather prediction, something must have changed, because now they were predicting most of our landing locations were actually going to be in this mountainous region. So we decided to axe site number 1 and call that basically not too viable. We then looked at sites number 2 and 3, and we saw that, yeah, both of these were pretty reasonable, although these sites to the further north did seem to drift farther north, which means we would have to drive further and further away. So this led us to basically site number 2 as our actual launch site. Now, what's interesting that I do want to show you is, let me go ahead and comment out some of the sites number 1 and 2, and let's just look at site number comment out the sites number 1 and 3, and just look at site number 2, which is the location that we were going to actually go with. So let me just pull that up again on our other plot, and here it is. So we are going to launch now right next to the Columbia River, and we see most of the trajectories are just going to float to the north east and land hopefully in this kind of flat terrain. So this was nice. The one thing that's interesting that I do want to point out is notice that some of these trajectories end up here in Ephrata, and this right here, let me zoom in, is the Ephrata Municipal Airport. So these were some pretty off nominal conditions, so we weren't anticipating that it was going to land there. We were pretty confident that it was going to land in, you can see there's a lot more trajectories that land down here. So we were pretty confident that this was going to turn out pretty reasonable, but again, I want to just bring that to your attention now because this is going to come back to us later in the story. That being said, this is a regional airport. We saw that all of our landings were very far away from the Grant County International Airport. This is a much bigger airport, so that was good, right? Okay, so with this information in mind, we basically have a reasonable idea of where the balloon is going to go. We know we are going to launch from, and I think we're pretty much out of the mission planning phase, and it's time to start talking about the actual mission execution. So in terms of the actual mission execution, there's a couple of things we want to talk about. So the first is, how did we go ahead and source the helium that we're going to use to fill the balloon with? Next, let's talk a little bit about some of the logistics and equipment before going into the actual meat and potatoes of this discussion, and that is namely the launch and the recovery of the system. All right, so let's talk about how are you going to get the helium that you're going to need to fill your balloon. So one option is to just go, and if you go to like Target or any other kind of website, you can find they have these disposable helium tanks that you can buy that are designed for mostly, kids' birthday parties. Here's an example of it, and you can see that if you spend $30, you'll get this non-refillable disposable canister, which has about 9 cubic feet of helium. Now, while this is a feasible route, it's far from ideal because if you remember, our balloon was going to take about 131 cubic feet. So we're actually going to need about 15 individual bottles of this to get to that number. And if you take $30 times 15, you're talking about $450 worth of helium. So you're paying about $3.37 per cubic foot of helium. And what I think is almost worse, first, I kind of feel bad about using the helium because it's a kind of non-renewable resource. But now you also have 15 of these empty containers that are just going to go into the landfill. So again, I'm not thrilled with this idea, and I've seen some people suggest this as one way to go, but I would highly recommend against going and trying to buy these small canisters and using it to fill your weather balloon. So the much better route is to go and actually find a supplier that is able to sell you larger volumes of helium. And surprisingly, you may want to investigate welding supply stores. So in my area, there is a chain called Central Welding Supply, and they supply, obviously, as the name might suggest, welding equipment and supplies. And helium is actually a gas that is used by welders quite regularly. So this is an excellent place to go. And actually, I went and talked to them. They were super friendly, and they helped me find 2 different ways to get helium from them. So the first way is you can buy a cylinder from them and they will fill it with helium, and you can basically purchase it and you have it forever, and it's yours to keep. You get to keep this in your garage, and you can start your own balloon party company by filling kids' balloons in your backyard. So this is actually what I ended up doing, is I went and I bought an 80 cubic foot cylinder of helium. So the way that works is they're going to charge you about $340 for the empty cylinder. And again, you are purchasing that cylinder, so you get to keep it for as long as you want. Then they'll fill it up with you with helium for about $100, and then they have a very small hazmat charge. So in general, overall, what I ended up doing here is, you can see it's still kind of expensive, right? This is now $340 total to get 80 cubic feet of helium. So this actually comes out to be more expensive than the party balloon perspective if you're looking at this from a pure dollars per cubic foot of helium. So this is one way to go, and it's not the most economically viable, but it has the benefit of you get to own the cylinder and keep it and use it for as long as you want. That becomes relevant if we start looking at the second way you can go about doing this. So the other way that a lot of these places will let you obtain helium is they will basically rent the cylinder to you and fill it with helium or whatever gas you want. Now, in this case, what I did was I rented a 125 cubic foot cylinder from them, and you can see what they charged there was just $125.50 for the rental of both the cylinder and I guess you can call it the purchase of the gas. Now, the reason why I'm kind of hesitating on that is because you have to use up all of the helium. They're not going to credit you back if you only use half of the helium and return the tank half full. You basically got to use it or lose it. So in this situation, you can see I paid about $130 to get 125 cubic feet of helium. And in this case, this is significantly better from a financial economy perspective, right? So it's $1 per cubic foot of helium. The caveat with this is they are not going to let you keep that cylinder for very long. I had to beg them to let me hold on to it for 2 weeks. So if you combine this with the fact that helium, it's getting to be kind of a rare resource and it's hard to get your hands on. So I actually had to call multiple stores to find one that was willing to rent me this helium cylinder in this configuration. So the timing was kind of tricky because I had to find a store which had the helium in stock within the 2-week launch window of our adventure, right? And the other issue is, if you see right here that this 125 cubic feet is not enough to fill the balloon. I wanted some buffer, so that's why I rented this helium cylinder that was 125 cubic feet. I knew that we were going to use it up completely and completely run it dry, but then we could top it off with the 80 cubic foot cylinder that I had purchased. So I could just use, 10, 20, 30 cubic feet out of my personal cylinder, right? That's action number 1 or option number 1 up top. And then I would have a partially filled helium cylinder, which I could then keep at my house for as long as I want. So if I wanted to do this again in the future, I would have a partially filled helium cylinder, and I could then again try to go rent a cylinder, and then basically it gives you a couple more options by buying your cylinder. So again, this is probably the major expense, right? If you look at this here, you can see it's almost $500 of helium to get this off the ground, pardon the pun. So, long story short, this is kind of what I would suggest. If you are going out and you know exactly when you're going to launch, you know you're not going to have to cancel or postpone the mission, then renting the cylinder makes a lot of sense. Especially if you can get a cylinder which is big, about the size of your balloon. The only problem is, again, that'll give you like one shot. It's going to give you not a lot of wiggle room for mistakes. So you may want to consider also buying a cylinder to augment the rental cylinder, just to give you a couple of more options. So anyway, this is the route we went. We purchased a cylinder and we also rented a cylinder for this excursion. Alright, so now we're getting really close to actually launching, and one of the most important things that you can do to make sure that your launch is safe and visible to other aviation traffic is to file a NOTAM, or a Notice to Airmen. So I've included the phone number up there, and I've also included a sample of the verbiage that I gave to the NOTAM office so that they could post it. So you can see right there in the middle of the screen, this is what we told them about our launch, and they then put it into the FAA's NOTAM system, and you can see our NOTAM show up down here, and that is now available to all aviators that are in the area, so they'll know that we have a unmanned free balloon that is going to be floating up through potential traffic and airspace where other aircraft may be at about this certain time. So again, this is a very important part of the operation to make sure that it's safe and visible to other airmen. So the next part of the mission execution is really to start writing down all of the relevant information about the launch. So one of the things that's very important is obviously a rough timeline of when we anticipate doing things. This is going to help all the participants coordinate. So as you can see, our general idea was to basically leave Seattle early in the morning, spend a few hours driving out to the launch site. We timed it that it should take us about an hour to set up all of our infrastructure and get the balloon ready to launch. And then as we saw earlier, it's going to take about 2 hours to ascend and burst. And what we decided to do is, since we had a lot of kids involved, we decided to basically have lunch at the launch site and track the balloon as it ascended, and just give the kids a place to eat and have some fun and basically watch the balloon go up and then start chasing it. So we anticipate the balloon is then going to burst around 2 p.m. and then hopefully spend an hour descending before landing around 3, and we don't know where it's going to land. We saw some of those trajectory predictions, and some of those might involve hiking out into the woods, so we budgeted at least 2 hours for recovery. Luckily, this was in the spring where it doesn't get dark until quite late, so we're hoping to be able to recover the payload by 5 and then hopefully arrive at a hotel or campsite in the evening. And then we were going to spend the night out there and then come back to Seattle the next day. So this was our general timeline. So the other important part of the actual execution was making sure that we packed all of our equipment that we need. So here's a sampling of some of our packing list of all of the different equipment that we needed to bring with us and basically set out at the mission launch site, and make sure that we have it all ready and easily accessible so that we can get it into the flight vehicle and ready to go. So we basically packed all of this into our giant van and shoved it in there and started driving out. One other thing that was very helpful is we also assigned specific jobs to every participant, so they knew exactly what they needed to do. So we talked about some of these jobs earlier, like the helium tank operator, the balloon neck technician, etc., etc. But we also decided to include a job of a dedicated checklist manager. That's number 7 you see there. This person was in charge of making sure that we ran through the checklist and did not skip any steps, and everything was properly executed. We also had a videographer on hand to make sure we captured all the great video and footage that you see here so we can document our experience. And then we also had 1 or 2 ground station technicians that were going to be sitting in front of our laptop watching the APRS packets and tracking the balloon during its ascent and descent. So this finally takes us to probably what is the most important bit of documentation in this entire operation, and that is the actual checklist that we used on the day of the launch. For those of you obviously who have been in flight testing or any sort of outdoor data gathering, you know that checklists are incredibly valuable, and we spent a lot of time refining this and working out some of the bugs so that on the day of the operation we basically just had to walk down this checklist top to bottom to make sure everything worked well. That being said, I think it's worth talking through this, especially because I'd like to call out a couple of areas where we either missed items and that had consequences later on, but I think it is valuable just to talk through each item. So this might be a little bit of a longer discussion, but I hope it's valuable to you. So the first set of operations in our checklist all were related to our preparation before we actually left. So obviously weighing the components was important because that allowed us to get all of those calculations we talked about earlier. We then conducted a full flight readiness review with all of the participants involved. So we basically briefed everyone about the things like the timeline, this checklist, the inflation procedure, all of that stuff, so that everyone knew what was going to be happening all the way from start all the way to recovery. We then put together this entire mission document. You can see it's a 19-page document which has all the information that everyone would need to know about this actual launch. And then we conducted all those trajectory predictions we talked about earlier and allowed us to select the launch site. We then were able to coordinate logistics with all of the families that were involved with the launch. And we also did things like record relevant parameters like the amount of helium necessary, the anticipated ascent rate, things like that, and also shot some video that we're actually showing in this particular video right now. Lastly, we did run some of those launch day predictions, right? These were those last trajectory predictions that allowed us to pick which site we were actually going to launch at. And as we just talked about, we also filed a NOTAM with the FAA. Next, once we arrived at the site, we had to prepare the site. So we set up all of our tables. We actually carried several pop-up tents for some sun and or rain shelter. We then laid out our tarp for the balloon. We set up our helium tank, our concrete anchors, and the weights were all ready and in place. We talked about all of this earlier. We also put our payload equipment on a separate table and had that all ready and in place. And hopefully when we were ready to go, you just need to turn things on. And then we just made sure that the valve was closed, and then we were ready to start inflation. So I don't think we need to talk through the inflation procedure too much because we already discussed that with graphics. This is basically the process we talked about earlier. The only thing that maybe we'll call out that deviates very slightly is we are attaching what we're calling a 50-meter ascent rate line to the primary loop. So we're going to allow the balloon to fly up 50 meters on a tether. And what we're trying to do during that is we want to time how long it takes just so that we can know what the actual ascent rate of the balloon is, because that's going to be critical in terms of our trajectory prediction and knowing how long it's going to take to reach altitude and pop, right? So that's pretty much the only difference. Otherwise, it's pretty much the process we talked about earlier of attaching, filling it up to a reasonable size, then attaching this dummy weight and the dummy positive lift weight. Basically, these two together should allow the balloon to be neutrally buoyant. And then we were able to basically get ready to start putting on the payload. Once we have verified that the balloon was inflated to the correct size, it's basically ready to fly. And it's now time to start preparing all of the payloads. So let's talk about what goes into our payload. So obviously we talked about this earlier. We had our spot trace unit. So we installed it, turned it on, and then the nice thing about the spot trace unit is they actually provide a URL for you to go to, and you can see exactly where that piece of equipment is located. So I've obviously blanked out the URL for my unit, but when you sign up with your spot trace unit, you will have a unique URL that you can go to. And this actually is going to be critical when it comes down to recovery. It turned out we heavily relied on the spot trace to recover the payload. After that was installed, we then put in the AirTag, and we verified that the AirTag was able to talk to a phone and track its location. Again, this is not a good tracking system. We were not going to be depending on this. This really was our third string backup. Our second string backup was our APRS tracking unit. So we installed that, and we made sure that all of the LEDs and the buzzers were operating properly. We made sure that we were able to hear the packets being broadcasted by the APRS tracking unit on our ham radio. And then we verified that we were actually able to decode those packets on our ground station and visualize it and track it from the ground. So that hopefully gets all of our tracking ready to go. Next, then, we got our GPS logging system installed, turned on, and we verified that it was collecting data. Then we installed our science. The science payload in this case, it turned out, was actually, we installed some candy. The kids wanted to send candy up to the edge of space and eat candy that was at a higher altitude than any other candy they had ever eaten before. So the science payload for this was, I think, a bunch of M&Ms and Skittles, actually. So that was just installed. All right, now we're on to the camera equipment. So this is where it gets interesting. So the Canon S100, like we said earlier, this is our still camera that is just going to be periodically shooting pictures every, I think we had it set up for every 45 seconds. Yes, every 45 seconds. And again, because it was running CHDK, we had to go through this sort of longer procedure to make sure that we had the proper script loaded. We had to make sure that it was shooting pictures, and it looked like it was acquiring data before we installed it. So again, we did all this, and I do want to just call to your attention that this was all working fine when we installed the camera. And you're going to see later on that it did work, but not flawlessly. We'll talk about that later. Okay, now let's come on to the video camera. And this is where I think we missed something. So you notice all this seems reasonable, right? You want to clean the camera, you want to put the camera in, you want to ensure that the recording settings are appropriate, and you want to verify that it's collecting data. Notice the one thing we missed in this checklist, we should have added a step that says erase the camera SD card to make sure you're starting from a blank card. So that's one thing that we would do differently, is put that in, because it turned out our SD card was actually already half full by the time we turned it on. So this made it so we weren't able to capture the full flight. So again, this is one place that we goofed up and probably should fix it in the future. You know, and come to think of it, we probably should have also added a step on the Canon camera to reset and or reflash and erase all the pictures before starting. So both of the cameras, we probably should have erased the data before we started. Okay, now we're on to this. After we installed the camera, we basically have the payload box ready to go. It is collecting data, it's shooting pictures, and we're ready to launch. So what we did now, this next step in the operation is all focused on making sure that the ascent rate of the actual balloon is close to what we anticipated. So what we did was, if you read through these steps, it's basically saying just attach this 50 meters of line to the balloon and then just let it go. We're going to release the balloon and time how long does it take to get to a 50-meter altitude, and then just make sure the ascent rate is reasonable. If that is true, we then reeled the balloon back down and attached the safety leash, and then just got ready to launch the balloon. So this is actually not that bad. The only thing that's kind of interesting about this is we did bring a drone to videotape the actual launch location. So now's the time to launch the drone, because we're basically getting ready to go. As soon as the drone was in the air, we basically removed that 50-meter ascent line, because now we don't want it tethered anymore. We are going to let it go. We removed the safety leash, and then here is the big payoff moment. This is when we just launch the balloon, you let it go, and you monitor it, cross your fingers, and hope that everything's going to go all right. Once the balloon is up and away, we then moved into sort of our mission monitoring section of the mission. So what we were able to do is periodically monitor where the balloon was using the APRS packets, and we used a program called Direwolf. And again, we have a dedicated video talking about how to get Direwolf set up, how to use it for APRS tracking, all of that kind of good stuff. So we have other separate videos talking about how we were able to do this monitoring via the APRS tracking system. And once it's in the air, and as it starts to move away, we started to drive and follow it just so we could stay within broadcast range of the APRS tracking system. Hopefully what that'll allow us to do is track this all the way up to burst and to the actual landing. So once it lands, we are now into our payload recovery mode. So once we figure out where it lands, what we did was we wrote down the coordinates that we received from the spot trace units. We also recorded the landing coordinates from the APRS tracker, and then all it is once it lands, you just have to develop kind of some strategy to go ahead and recover the payload. So we talked it through with our team. We wanted to make sure that if it landed on somebody's property, we wanted to go and make sure we were able to talk to the landowner and obtain their permission to get onto the land. You're going to see that this is actually kind of interesting how it happened for us. And then once we had that permission, we went and just recover the payload and then turn off all of the equipment. And this was another critical one. We did want to make sure that we inspected everyone for ticks on your feet or legs, because a lot of the brush in this area, we anticipated potentially having to walk through high dry grass to recover the payload. So make sure that everyone is safe before downloading all of the data. And at that point, we're pretty much done. So let's see, how did this actually go in real life? So here we are at the launch site. With all the prior planning, the setup and launch actually went fairly smoothly. As you can see, we had a lot of cooks in the kitchen, and it really helped that everyone had an assigned job and knew exactly what they needed to do. Here's a quick time lapse of the entire process, and it really only took us about an hour to set up and get ready to launch. I thought it might be fun to look at some of the more critical portions of the launch in greater detail. For example, here you can see the kids attaching the dummy payload weight and the dummy positive lift weight, and then checking that we achieved neutral buoyancy. As you can see, we got a little excited and filled the balloon a little bit too much, but this is just going to help with our ascent rate, so we decided to leave it. And speaking of the ascent rate, here's the kids performing the ascent rate test. We measured out 50 meters of line and then timed how long it took the balloon to ascend that 50 meters. With a little bit of math, the kids backed out the ascent rate, and once we verified that it was reasonable, we reeled the balloon back in, removed the 50 meters of line, and got ready for the actual launch. This involved letting all the kids hold onto a string and then letting them perform a countdown to launch. And we're off. And here's another view of the launch to give you another perspective. So this is a selection of clips during the ascent. I'll leave a link to the entire flight in case you want to watch the unabridged version. You can see the stats on the various gauges on the display. If you're interested on how I overlaid all of this data, feel free to check out the series of videos on Dashware that I've got on the channel. We'll talk about the actual data acquisition and what we obtained during the flight, but for the moment, I just want to draw your attention to the surrounding environment. As you can see, we launched on a somewhat cloudy and overcast day. There was a little bit of a breeze near the surface, and you can see it swinging the payload box around a bit, and you can hear the creaks of the monofilament lines as we ascend. Now, as we climb higher, we actually get to enter into the clouds, and you can see some of the rain and condensation in the cloud accumulate on the acrylic bubble. Unfortunately, you can't really see too much here, and it's kind of interesting to note that you really can't tell that we're over 10,000 feet high at this point. And as we get up even higher, now we're around 30,000 feet, we actually break through the clouds, and I really just want to take a moment to just marvel at how beautiful it is up at this altitude. The skies are blue, you really can't hear too much wind, and in fact, if you just listen, you can barely hear anything. It's just peaceful and serene. It's also interesting to note that it's, negative 20 degrees Celsius outside, and you can see that the condensation we picked up when we were ascending through the clouds has actually frozen on the outside of the dome. Again, I really wish I had remembered to clear the SD card before we launched, because this is pretty much as much video we got before the SD card ran out of space. Again, I think I should just stop talking right now, and let's just take a moment to admire all of this beauty. So now that the balloon is up, we switched from launch to tracking mode. We immediately jumped over to our ground station to monitor the APRS packets, and this worked surprisingly well. We'll talk about this in greater detail when we discuss the results, but in short, we were able to hear packets for a large portion of the flight. All right, so here we are. So the balloon is in the air. Let's see, where is it? Yeah, 27,000 feet. So it's pretty far away. We're still hearing APRS packets, so that's good. So yeah, we launched down here in Vantage, and yeah, the balloon is all the way up here, kind of out here near Gorge. I think we're going about 30 miles an hour ground speed, so that's kind of interesting that we're still getting packets loud and clear. Unfortunately, the same couldn't be said for the spot trace unit. For whatever reason, as soon as it took off, it basically stopped working. So the only position fix we had was at the launch location, and it never updated during the flight. We continued to monitor the first portion of the ascent, and during this time the kids ate lunch while the adults packed up the gear into the cars, and we started to then chase the balloon. Here's some of the dash cam footage to show you what the terrain looks like. As you can see, it's pretty dry, arid, desert-like conditions with some farmland sprinkled in between. We actually lost direct APRS contact with our balloon when it drifted too far away. We were hoping that other stations or repeaters in the area would hear our balloon's packets and rebroadcast them to the internet, but it turns out that we actually weren't filtering on the correct call sign and SSID combination when we were looking on APRS.fi, and as such, we didn't have direct contact with our balloon for a few hours. We decided then to drive to a park that was about 30 miles away that was in the direction of the balloon's travel in an effort to re-establish radio contact. We arrived at the park and started listening for packets again, and it was at this time that one of our party members discovered that if you add the SSID suffix to our call sign when searching on APRS.fi, we would actually pick up the packets that were heard by other stations or repeaters in the area. So we saw this and actually discovered that the balloon had already burst and was rapidly losing altitude. So needless to say, we quickly packed up everything, jumped in the car, and started chasing it. And this is where the story takes an interesting turn. Out of all this vast empty area that the balloon could have drifted towards, we saw that it was actually headed towards the Ephrata Municipal Airport, which was over 40 miles away from where we launched. To make it even more interesting, as we started approaching the airport, it became more and more likely that the payload box was actually going to land inside the airport. Alright, so here we are chasing the balloon, and I think it just landed. We were monitoring it on the APRS tracking, and you will not believe this. Look at this. I can't believe it. It is like smack dab in the middle of the Ephrata Municipal Airport. And in fact, we also just saw the spot trace unit also just wake up. Let me pull that up, and look at that. It also thinks it is in the airport. So I think we're heading to the airport now to see if we can talk to someone and see if we can recover the payload. Here's a sign for the airport. Yep, here we are. Here's the airport. Okay, so theoretically our payload box is somewhere in there. All right, let's see if we can meet up with all the other people and go and talk to someone about getting access to the runway. So we gathered our entire group in the parking lot of the airport, and while the kids stayed back behind the fence, I went in to see if we could find someone to help us recover our payload box. It turns out that this is a small municipal airport, so there usually isn't too much activity, but on this particular day, they were actually hosting a glider competition, so there were a fair number of pilots around, and they directed me to the airport manager. He was a super friendly guy named Mike, and he was eager to help out the kids. We jumped in an electric cart they have for getting around the airport, and we headed out to the location indicated by the spot trace unit. It turns out that this was, pardon the pun, spot on, and we were able to drive right up to it. I was actually able to do a video call with the kids who were back behind the fence so that they could see the recovery live. Oh yeah, look at this. Mike found it. Mike found the box. There it is. There it is. Oh man, that is too great.
All right, go get it.
Oh,
go back.
Thank you, Mike. Okay, all right. All right, so here it is. Let's see if we can go pick it up. Okay, you got it?
Okay.
Quick, quick, quick. Is this it? Look at this, ladies. Here it is. Look at that. There's the balloon. Parachute. Here's the box. You can hear it beeping at us, guys. Look at this. Yeah, Mike found it on the first try. Here it is. Okay, I gotta hang up, guys. All right, we'll be back in a sec, okay, ladies? Bye.
I'm officially. Okay,
it's pretty bad. Chris, I saw you through the binoculars, and I saw you pick it up.
Check it out. So see what happened. Spread it out.
Can we open it? Chris, I saw you through the binoculars.
So after returning with a payload box, the kids were thrilled to tear it open and inspect the contents. I thought they would want to see the pictures and the data logs, but they were mostly interested in the candy.
Where are the Skittles? In that.
I suppose in hindsight that's not really surprising, and actually upon further reflection I suppose this is actually the highest altitude food that any of us had ever eaten, which is I guess kind of cool. And with that, this is the end of the mission execution phase of the project, and we should turn our attention to analyzing the results. So to start, here's a visualization of the entire trajectory in Google Earth. The data that was used to generate this was taken from our Arduino GPS data logging device, and we'll take a closer look at that later, but for now, I want to start with a, pardon the pun, high-level overview of the trajectory. And as you can see, down here is our launch point right by the Columbia River here near the Vantage Beach Park. And again, you can see it floating up, over, and then finally bursting, and then coming down, as we saw earlier, smack dab in the middle of the Ephrata Municipal Airport. So this is the overall trajectory. We'll talk about the statistics of this flight in a little bit, but I do want to just use the Google Earth visualization because I really like how it shows a sense of scale. So for example, if we zoom out, you can see, here's all of Washington State right here. You can see Seattle over here. You come across I-90, here's Snoqualmie Pass. You can see here's all the Cascade Mountains that we were trying to avoid, right? And you can see all the greenery and the forest over here. So we came over to eastern Washington where it's a lot flatter, a lot drier, a lot less stuff to conflict with. And you can see our overall trajectory was, a non-trivial amount of the state of Washington. And again, in fact, if you keep zooming out, you can kind of see in terms of the amount of the entire United States. Again, it's not small, and it's really kind of cool that you can see all this so easily. And in fact, let's zoom back in, and in fact, let's take a look at the altitude. So let me go ahead, zoom in, and let me see if I can tilt the map a little bit so we can see the altitude. And now you get a real nice sense of scale in terms of how high up we were, because again, if you just look at this, you can see some of the mountains over here. Here's Mount Adams, Mount Rainier, Mount Hood. There's all of these other. Where's Mount Rainier? All right, here's Mount Rainier. So we are way, way, way higher than even the highest mountain in the entire state of Washington. And again, if you zoom this out, it's just, I think this is just amazing. It's just so cool to see how high we went with respect to the overall altitude and topography of the region and just Earth in general. Look at this. We are literally getting out almost to kind of near the edge of space. Again, that's probably a little bit of hyperbole because, as we know, 100 kilometers is the edge of space, and we're nowhere near 100 kilometers up. But again, this is really kind of neat because it does show just the nice scale of the overall trajectory. So this is pretty darn cool, I think. So again, let's take a look at this. It's kind of cool to see from when we launched. You can see right here, we launched right here at this Ginkgo State Park, and for the most part, we did go straight up. This doesn't look like a lot of movement, right, laterally, and instead, it did take a little while. It was blowing a little bit, you can kind of see, and when we got to a little bit higher altitudes, we did pick up some horizontal velocity, right? You can see that right there. And yep, it just floated up and kept going, kept ascending, and now really, wow, up here when we got a little bit higher, it really did pick up speed and start moving quite a bit. But we came up, and then we finally burst, and then we fell down. A lot of this data, we're going to talk about this later, is it's not actually this straight. We lost data telemetry for a little bit, but yeah, I think you get the point. And then you can see it fell pretty straight down once we ended up here, and again we landed right here in the middle of the Ephrata Municipal Airport. So look at that, right off of the edge of this. I think it's an unused taxiway, right? So that is pretty cool that you can see all of this from this Google Earth visualization. So again, let's maybe go ahead and look at this from a flat viewpoint just so we can see it again. So this was our overall trajectory to give you a rough idea of what it looked like. And again, this is neat, right? We flew over all of this farmland, and again, I really enjoyed this. This was really cool to give you a high-level overview of what the mission looked like. So with that being said, let's go ahead and take a look at some of the stats, the high-level stats of things like altitude, duration, all that kind of good stuff. All right, so let's take a look at some overall stats of the entire mission. So I tried to put together a couple of slides to make this a little bit easier to consume. So some of the things that we care about, obviously, are, everyone wants to know how high did we actually reach. So look at this. According to our data logging system via GPS, we reached almost 81,000 feet. So that is pretty amazing in my opinion. What's even more amazing is if you compare this actual altitude to the predicted altitude. So up here, this table is sort of the predicted values that we computed ahead of time using various sources. And look at this. These predictions claimed 81,300 feet, and we pretty much got there, almost within 500 feet of the actual altitude. And I just find that amazing that the prediction was that accurate. Now, the burst altitude was accurate, but the actual ascent time and rate was maybe a little bit off. So you can see that the actual ascent took a little bit over 2 hours to go from launch all the way up to burst. Whereas the predicted case, again, remember this table here is sort of these nominal values that we predicted several weeks in advance. So I guess the ascent rate could possibly be different depending on environmental conditions. So you can see that the ascent time here was, about 100 minutes, whereas we actually did about, maybe 25 minutes more than the prediction. The descent rate also was a little bit off. We descended a little bit faster than we anticipated. We'll take a look at that in a second. But long story short, our whole mission took about 150 minutes from launch to landing. So here's the rough profile, and we're going to take a little bit closer look at this in a second. I just want to look at some of the high-level stats to start. Let's go on and talk about temperature. So remember, we had temperature probes on board, and again, high level, here's what ended up happening. The outside temperature, which you can see is sort of this blue curve, that got down to really cold. Look at this, minus 46 degrees Fahrenheit. And the inside of the box, though, did stay quite toasty relative to the outside. It stayed quite a bit warmer, 40 degrees warmer. And it only got down to 7 degrees Fahrenheit, which still is pretty darn cold. And again, we'll take a closer look at these temperature profiles in a second. How about the ascent and descent rates? So as you can see, the ascent rate was kind of interesting. Here you can see we're prepping, and then we launch, and then you can see the ascent rate sort of varied over time. I've just drawn this bar here to show what an ascent rate of 14 feet per second, or around 9.5 miles per hour looked like. And you can see that was, going, and then it burst, and then we started dropping like a stone until the parachute picked it up, and we started kind of slowing the descent rate. So again, this was a little bit off from the predictions, and I don't think that's that bad. But I'll just give you a little bit of some of the numbers here. It seems like, here are some rough parameters, and again, we'll take a closer look at these in just a moment. But the overall trajectory, a lot of people want to know, how far did the balloon go? Well, it turns out we traveled about 33 miles as the crow flies from launch to our landing site. And obviously the balloon traveled a little bit more if you take all of these kind of wiggles and turns into account. But roughly it landed 33 miles away from where we started. Now, all of this is pretty interesting, and maybe what we should do is let's compare this to some of the predictions that we ran on the day of the actual launch, because those are much more likely to be accurate. So to start, let's start looking at this maybe top-down two-dimensional trajectory. In fact, I'll bring up my MATLAB script that I wrote to kind of parse the data. And again, the blue line is the actual trajectory, and this red line is one of our predicted runs coming from that trajectory predictor. And again, let me pull up the data sheet, and I'll just say that this is data set number 14. So this is assuming we launched from Vantage Beach, and this is the prediction that we ran on the day of the launch, just several hours before we actually launched. And we ran it with all of our nominal parameters here. So this is sort of a nominal case. What's interesting is one thing that you can note here is the slight discrepancy in our launch location. So the prediction, which is the red one, like we said, we assumed that we were going to be launching from that Vantage Beach location. And let me zoom in and I'll show you a little bit. Whoops, that might have been too much of a zoom in. Let me zoom out a little bit so we can see this a little bit easier. But we assumed and scoped out ahead of time this location, which was right on the Columbia river. And hopefully this map is going to load in so you can see this a little bit better. Aha, there it goes. Okay, so again, the red is the predicted, and we assumed that we were going to be launching down here right on this park. When we got there, the launch location wasn't super great. There wasn't a lot of room to set up and things like that. So we actually found another little park, which was, as you can see, just a little bit north of our predicted location. So the blue line is where we actually launched. So you can see immediately there's a small discrepancy in the launch location, but it's not a lot. And as you can see, what's interesting about this is that the prediction is pretty darn close to the actual. And again, you got to remember, the red line was predicted, and we ran this prediction just several hours before we launched. Now again, this red line doesn't have the exact launch time. It doesn't line up exactly with when we actually launch, and again, that will probably account for some of these discrepancies. But again, what's fascinating about this is I look at this and you see that the red line, it actually did predict that we would land a little bit south of the municipal airport. And the fact that we launched a little bit north of where we predicted, I bet if we had ran this prediction for our actual launch location, again, look at this, it would probably be pretty darn close to the actual location, and it might have told us that, yeah, you are very likely going to land in the airport. So again, I am just surprised how well this trajectory predictor seemed to perform in this case. Let's look at altitude. How does the altitude profile look like? So here is again our altitude profile. So the blue is our actual altitude profile versus time, and the red is the predicted. So again, this is where it turned to be a little bit off. So the predicted, it's assumed we were going to ascend a little bit slower than we actually did, and therefore that the mission was going to take a little bit longer. But again, you can see general trends are correct, and the thing that I am just shocked at is the actual altitudes are almost bang on. Those are almost spot on. Now, how about the descent rate? You can see that we predicted we would burst at different times, so the descent rates are a little bit harder to line up. In fact, you know what might be easier is let me just shift this red curve so that we match the time at burst. So let me go ahead and hold on a second. I gotta just switch some code real quick and rerun this thing. Let me do this real fast and rerun. Give me a second and I'll pull up that figure again. Okay, so here you go. So you can see here is if we match at the burst time, you can see that the red is a predicted trajectory, the blue is our actual descent. So the actual descent, we descended faster than we actually thought we would. So I don't know if the parachute got tangled or maybe we were just heavier than we thought we would be. But the parachute didn't perform as well as we anticipated, and we descended a little bit quicker than the prediction. But again, that isn't too much of a big deal. So if you combine both the altitude profile with sort of the lateral longitudinal or lat long trajectory, let's create a three-dimensional plot to just look at the actual and predicted trajectories. And again, you look at this thing and I am just amazed. Again, the blue line is actual, red is predicted. So if you look at this guy, they just look really darn close. So I think, long story short, that trajectory predictor is fairly accurate, especially if you run it close to the actual launch time so that it has good predictions on the weather patterns and the wind fields and things like that. And as long as you get your ascent and descent rate and other parameters fairly in the ballpark, again, look at this. This worked out amazingly well. So now that we've taken sort of a high-level look at the detail or at some of this data that was collected via the Arduino GPS and data logging device, let me pull up another MATLAB script and let's go through some of the actual collected data in a little bit greater detail. All right, so let's take a little bit closer look at some of the data that we collected via the Arduino GPS data logger. So as you can see, we're basically writing all of the relevant parameters to just a giant CSV file, and we wrote a little bit of MATLAB code to parse all of this and make it a little bit more intelligible. So let's take a look at that now. So here is the altitude profile that we recorded during the mission. So as you can see, we launched down here and you can see it ascended. Now what's interesting about the ascent is if you look at this long enough, it looks like the first part, there's an ascent right here where it's rising fairly quickly, and then the ascent rate actually slows down. So I don't know if that's just due to changes in atmospheric properties which slowed the ascent of the balloon, but for whatever reason it looked like it did not have a uniform ascent rate the entire time. Now, what's interesting is up here you can see that we've got a flat spot here in the altitude profile. Now, the reason this happened is because this altitude, I probably should have been a little bit more specific on the y-axis. So this is GPS altitude. So what I believe happened is we were ascending, and then up here the balloon burst, and at that point it probably started tumbling, right? The payload box would have started tumbling, and I believe we lost the GPS lock here. And in fact, what we can do is, let's go ahead and zoom in and look what time this actually happened. So if you zoom in on this, we see that we actually had a burst here at about, what was this, 3:26 and 16 seconds local time in the afternoon. So keep that in mind, 3:26 and 16 seconds is when we think the balloon actually burst. So it burst, and then while it was tumbling, we did not have a GPS lock. And what I believe probably happened was that eventually the parachute would have deployed and would have fallen into a region of atmosphere where there was enough atmospheric density to make the parachute have some actual effect, and therefore it would have righted the payload package. So the payload at this point probably would have been upright with the GPS receivers pointing toward the sky, and we were able to reacquire a lock down here. So over here is where we reacquired a lock. Again, let me see if we can zoom in on this just to get a better idea of when this happened. So yeah, it looks like we reacquired our lock at 3:34 and 18 seconds. So I mean, what's that difference? 26 to 34. What is that? 8 minutes? Did I do that math right? Is that 8 minutes? Yeah. So I guess we were tumbling without a GPS lock for 8 minutes until we were able to reacquire a lock here at around, what is this, 40,000 feet. So we had dropped quite a distance before we lost our lock, or before we reacquired our lock. So what kind of corroborates this discussion is, let's take a look now at the temperature profile. Now here's the temperature profile. And again, the blue is the outside temperature sensor, the red is the interior temperature sensor. And as you can see, as we're ascending, the temperature is dropping pretty drastically. It stabilized, it actually even got a little bit warmer. Now, you can see there's a drastic change in the temperature profile right here. Let's see what time this profile changed. And what's interesting is, again, look at this. This happened here at 3:26 and 16 seconds. So here is where we think the balloon burst, and when it burst, it would have started dropping precipitously through the atmosphere, and that's what you see right here. The temperature is starting to drop. Now what's really cool about this is, even though we lost a GPS lock, it sure looks like we were able to still collect temperature data. So the temperature sensor probes were still operating, which makes perfectly good sense. You don't need a GPS lock for it to log data. So we are still collecting temperature data, and as you can see, we're dropping like a stone here because the temperature is changing so rapidly. So yeah, I think that's exactly what happened. The balloon burst at around 3:26 in the afternoon, and we just started dropping and coming down through the atmosphere. Now, what's interesting about this temperature profile, maybe instead of plotting temperature on the y-axis and time on the x-axis, you know, for those of you who are engineers, I'm sure you are aware of the, the standard atmosphere model, right? There's the U.S. standard atmosphere model, there's the international standard atmosphere model, and long story short is, a lot of times you'll see this plotted with temperature on the x-axis and elevation or altitude on the y-axis. So we see that as you start rising in altitude, obviously the temperature starts going down until eventually there's a location here at around, 10,000, 11,000 meters where the temperature is actually just constant. And then if you keep going up in the atmosphere, the temperature actually increases. So what would be interesting is, let's overlay our temperature profile that we measured with this predicted, standard U.S. atmosphere. And let me see if I have a picture of that. So let me do that right here. So here we go. So here is our actual data here in blue, And then we have both the international standard atmosphere model and the US standard atmosphere model, which really don't differ too much until you get up here to higher altitudes. And I do like the US standard altitude model just because it does seem to predict what we experienced a little bit more. So in the sense, you can see that our temperature went down as we started increasing altitude, and then the temperature did kind of stabilize and remain constant, and then it even started increasing. So we actually started getting to this portion of the atmosphere where we were high enough up that the temperature actually started increasing. And again, you can see those effects. Now, one thing that I'm sure you're saying is, look at this, and there's quite a discrepancy in the actual absolute value of temperature, right? The trends are there, and we did measure that, but the absolute value is different. So I think one reason for this is, again, if you come back to our other temperature plot, where did I put that? Right here. Right there was an interior temperature and an exterior temperature. Remember, we had heaters running on the inside. We had electronics running on the inside. So the interior of the box was much warmer than the exterior. And I think the exterior of the box was also still much warmer than the actual ambient temperature because we were so close in proximity to the electronics and things like that. So again, I think if we were to repeat this experiment, what might be interesting is to dangle this exterior temperature probe outside, 2 or 3 feet away from the actual payload box, and I think we would get a better measurement and probably better correlation with the predicted standard atmosphere models. But again, what's important about this is that the trends seem to line up quite nicely. Okay, and while we're talking about tumbling and losing GPS lock, here's another set of data that we were able to collect that does also interestingly tell this story. So this is the number of GPS satellites that we had locked. So as you can see, when we started the mission, right, we let everything stabilize. We had 10 satellite locks. And in fact, as we started ascending, we even got more. We were up to 11 satellites. All this here, even 12 satellites as we got higher and higher. And then suddenly, look here, we dropped to 0 satellites. And again, if you look at this timestamp, I bet you this happened at 3:26 and 16 seconds, and there you go, right? That is exactly what happened, right? We lost the GPS locks because the balloon, because the payload box started tumbling, and it took a while before it to stabilize before we could reacquire a satellite lock. So again, I think what would be fascinating is if we repeated this experiment, it might be nice to put on something like an accelerometer or a rate gyro on board and measure that. And I bet we would see right here when the balloon burst, if we had rate gyros on board, you would see the angular velocity vector increase quite a bit as the payload box started tumbling when the balloon burst. So again, this is kind of interesting data. Let's look at something else that we can look at for GPS. So the GPS could also help get us speed. You could even get speed probably from finite differencing, but we also were able to get velocity. And again, this I think is what's interesting. This I believe is planar velocity in sort of the XY or northeast plane. So what's nice and interesting about this is you see that as we launched, we weren't going, it wasn't drifting horizontally that much, right? 5 miles an hour, but 15 miles an hour. But look at this. At some points, when we actually got up to altitude, this is when the balloon started trucking. Look at this. 25, 30, even our maximum speed was almost 37 miles an hour. So the balloon was really trucking horizontally. And again, that corroborates some of our, let me see if I can pull up our plot here, right? We saw this, that here you can see the balloon start taking off to the northeast, and according to this velocity plot, it looks like it's going at 30 miles an hour. So this is why in some situations I think you can get balloons which drift hundreds of miles, right? Ours only went 33 miles, but you could potentially get trajectories that are much further than that, right? Okay, so what else is interesting to look at besides altitudes? Let's see. We also had, here, vertical speed. Vertical speed is interesting in terms of feet per second. And again, this plot looks a little bit washed out because of the part where we drop. So let's zoom in just to the ascent portion of this. So I'm going to zoom in only here to the ascent. And this is a little bit more reasonable to look at, right? So here, the ascent, this is effectively giving us an ascent rate, right? So you can see here on the ground, and here is where we launched. And as soon as we launched, look at this, we got pretty close to, I believe we were looking at around 14 meters per second, feet per second was our goal. And look at this, this is what it did, right? But the ascent rate was definitely not constant over the entire ascent. In fact, we started going up quickly, and then for some reason it dropped all the way down here to, you know, almost 8 or 9 feet per second ascent rate until it burst. So now again, this is what's fascinating about the burst. Look at this. Gee whiz. When it burst right here at 326, look at our descent rate. Look at this. Woo, man. Again, I don't think you can trust this because this is probably from GPS, and we saw that we lost GPS lock, but that was, you know, yeah, that's ridiculous. 1,400 feet per second. No, that's probably not reasonable. Let's look at the descent rate when we actually reacquired the lock. So that's probably more like something like this. So look at this. So here we go. 60 feet per second, right? So yeah, that is probably when the parachute is caught at, right? It's going down at 60 feet per second. And again, what's really fascinating about this, right, is here we were up at around 40,000 feet where the air is thin, right? So the air density is lower, so the parachute isn't going to operate quite as well. But as we start coming down into denser and denser air, the parachute starts creating more and more drag, and it starts slowing our descent rate. So it looks like around here we hit the ground, you know, I don't know, 29 feet per second. That's, you know, not too shabby, right? Okay, and then let's look at, oh, actually, wait, that might be all of the data we have from our data logger. Yeah, I think that's most of the interesting data that we have from our Arduino data logger. So, long story short, we are pretty darn thrilled with how that Arduino data logger worked. It functioned pretty much flawlessly the entire trajectory, and it allowed us to get a lot of data over the entire mission. The only time it faltered was when we had the GPS lose lock right when the balloon burst, but otherwise this thing worked swimmingly well. So, with that being said, maybe we should turn our attention now to our APRS tracking system, which you got to remember, right? This data file and this data log is something that we acquired offline and after the fact, right? This was after we recovered the payload box. We were able to download this entire CSV file and analyze it, right? So, this is great if you're able to recover the payload box, but if for whatever reason you lost it, or in order to track the progress online during the mission, you actually need the APRS tracking system to send live telemetry back to the ground station. So we saw that worked pretty reasonably well, but now let's take a little bit more close look at some of those packets and see how it performed.
Alright, so as we saw, we were able to track and hear our APRS packets locally at our local ground station and decode those via direwolf and plot them via pinpoint APRS. But again, what we didn't do is during the actual mission, we didn't actually connect to the iGate, so we weren't actually forwarding our APRS packets to the internet for other people to see. Now, that being said, even though we weren't doing the forwarding, other people and other iGates and other stations in the area were able to hear our packets and forward it to the internet and, for example, to APRS.fi. So several people in our party were actually able to track the balloon via APRS.fi. So, for example, if we come here to my call sign dash, and this is one thing we discovered, is that not only do you have to put in the call sign, but you also have to put the dash with the SSID. So we were using 11 for our balloon. So if we search this, and let's look at how about the last 24 hours, and I'll make a tail link to 24 hours. Let's search this, and again, I'm doing this the day after. So APRS.fi, I don't think maintains a lot of this information for a super duper long time, so you may want to do this as soon as your mission is over just to gather this data. And in fact, you may want to then export it over here. I'll talk about this in a little bit. We saved all the raw packets and the Google Earth and things like that. But anyway, long story short, this is basically what was available via the internet during our mission. And as you can see, this is perfect, right? We launched from down here, and all of these packets were being heard by other stations in the area. In fact, if you kind of hover over it, you can see the little purple line. I think shows you which stations were able to hear your packets. And let me see if I can get this to show up. Come on. I think it's loading. There you go. See? So for example, during launch, we were heard by this station over here in Kittitas, which is several miles away. In fact, I'll look at that in a second. And as we were ascending, look at this. This station kept hearing us, and forwarding it to the internet, right? So it's forwarding all those packets through its iGate to the internet, so other people in our party and actually anywhere in the world could track the launch. So this was great. Even though we were tracking it ourselves locally and privately on our ground station via Direwolf, everyone else could do this as well. So look at this. This is great, right? It heard, and actually look at this. What's really kind of fascinating is, for example, right here, look, there was another station, this guy, WA2WA. If I look at this one, this is another one which is way down here in kind of the southeast corner of the state down here. So we were launching, over here. So you can see this was quite a distance away. And again, what's fascinating about this is super duper cool that other people were hearing our APRS packets and forwarding it to the internet. So all of these, as we're going along, yeah, this guy in Kittitas was super helpful. You can see a lot of our packets came from him. But here's another one right here. This came from this one, INDMT. This one we saw is really far away. Let's load him up. And look at this. He's clear in the other state. He's over here in Idaho, and we are way over here on the corner at Vantage, right? So that is, pretty good distance. We'll look at that later. Now, yeah, so during the ascent, all these stations were hearing us. You can see all over different stations. Here's some more stations. This guy was being heard by some stations further up north, I think in Kashmir. But you come along, and then, yeah, we did eventually lose packets. So you can see right here, there were a whole bunch of APRS packets that the balloon was probably broadcasting, but no one was hearing, or something went on with the GPS, it stopped. In fact, we had some issues. We're going to take a look at the data a little bit later. But a lot of these altitudes seemed a little bit off, but we had a big gap right here with some of these intermittent data points. And then down here, as the balloon was descending, we started picking it up again by some other stations. And let me see if this thing's going to load. I think it has to load up where the listener was. But anyway, a lot of these packets were being heard as we were descending into the airport. Again, I cannot believe that we ended up in an airport of all places, but that's something to discuss later. I actually plotted up a lot of these locations of these different stations that were listening and hearing us. So again, here's our launch site here in Vantage, right? And we saw that there was this station here in Kittitas, the town, a couple towns over, that was able to hear us quite well. And you can see that one was 20 miles away, right? But then we also were heard by this station up here in Kashmir, which is, look at that, now it's 45 miles away. And then we were also heard by this station down here in the kind of south east corner of the state, look, 112 miles away. And then what was super awesome is we were heard by this station way over here in Idaho, which was 160 miles away, and they heard one of our packets. So again, that was pretty neat. I did forget to plot one of them. I think there was one out way back here in Sammamish, actually, also, like 100 miles away, that also heard us. So anyway, I thought that's really cool that APRS.FI is able to show us all of this information of all of the different stations that heard us during our mission and forwarded those packets off to the internet. So that's pretty neat. And again, I would recommend getting this data sooner rather than later, because I'm not entirely certain how long the database is kept for. For example, I think, if you just look here in this drop-down menu, yeah, here 7 days looks to be the longest you can pick for the data. So you're going to want to get this right away. So anyway, the APRS, it looks like, was a pretty good success. It was a really good way of tracking it. I should mention, though, it didn't work all the way to the touchdown. So for example, I think this is like the last point that we heard. Let me see, or maybe this one here. This is the one that has altitude. Look at that, 3,600 feet. I think the airport, the surface here was about 1,200 or something like that. So, about 2,000 feet above AGL was the last time we heard a packet. Of course, the balloon was descending pretty quick, so I'm not sure how many other packets it would hear before it hit the ground and bent the antenna and probably made it so it was not very effective at transmitting. But anyway, this was our last packet, about 2,000 feet AGL, and who heard this one? This was this guy, K7. How far away is that guy? Let's look him up. Oh, this was the Kashmir one, so that was pretty far away. Yeah, so again, where were we? Where's, I'm trying to find Ephrata. Did I kind of mess myself up here? Yeah, hold on. Well, yeah, Kashmir here. I am totally turned around. Where is... Oh, there it is. Okay, here. Kashmir's up here, and yeah, the balloon is down here at the Ephrata Regional Airport. So, yeah, at 2,000 feet AGL, some guy way over here in Kashmir was still able to hear us. So, again, that's kind of cool.
Alright, so we saw that the APRS tracker that we built worked quite well. How about our other backup tracking system, namely the Spot Trace unit? So here I am on the Spot Trace website, and this actually, I will give them credit, this is actually a really nice interface. I can go here and I can load up and see pretty much where this unit has been pretty much any time. So I'm actually sitting here, this is almost 8 months after we did the flight, and I'm able to quickly just, you know, zoom in on the data ranges that I want and zoom in on the data. So as you can see, here we are. We were driving to the site, and you can see it's tracking every few minutes. We're getting a location, and then you can see it gets a nice data point here, actually multiple data points as we are kind of getting ready to go. And in fact, I think some of these might be, you know, almost right when we're about ready to lift off. Now, here's what's interesting about this is, unfortunately, the Spot Trace unit plain old got nothing during the flight. During the mission, you can see here's the launch data point, and then there is absolutely nothing in the middle. So as we were flying during the mission, I was trying to check the website to check on where the Spot Trace unit was, and it constantly said it was sitting here on the ground, right? We got no updates in the air. And I know that this unit is supposed to sense when there's movement and then kind of wake up and try to send a satellite packet up and to the server. I've seen that many times. When I'm driving around with this in the car, I'll get an email saying, hey, I noticed that the Spot Trace unit is moving. Here's where it's located. Well, it was definitely moving during this entire ascent, burst, falling phase, and unfortunately, it completely failed here. So look at this. We got no live data tracking via the Spot Trace when it was in the air. So unfortunately, that didn't work. Now, what's interesting though is, look over here. We did get some data as it was almost about ready to land. In fact, here, you can see, here's a spot where the thing was actually coming down and, you know, it was falling, it was descending. Remember the time we said the burst occurred at, what was it, 3:26 and 16 seconds? So look here, 3:42. So, you know, several minutes after, and it was on its way to falling and almost where it hit the ground. And in fact, this, I think, is the data point here where it hit the ground. In fact, let's zoom in. It looks like there's multiple data points here. Yeah, there's 2 data points here. So you can see that this is where we basically ended up. Let me see if I can click off this so as we can kind of, oops, I kind of want this data point here. Come on, show me the timestamp of this. This is a little bit, maybe I have to hover over this. It's trying to, it's got this silly, okay, there we go. 3:52. So this is where it was, and actually we did use the Spot Trace unit to actually zoom in on the location once it was down. So again, this unit was, I don't know, half failure, half success. It failed during the mission, but it came in and it was successful when it actually mattered, right? When the payload box landed, then it finally decided, you know, to send up some data, and we were able to recover it using this information. So that was good. And as you can see, it picked it up after we recovered it. We were driving along back here, so let me see if we can get a little bit more information on this data point here. Yeah, 5:02. So it looks like it was only sitting here for, you know, about an hour before we were actually able to come here, pick it up, and start driving back here, open up the box, and then you can even see we started driving more, and I think we stayed here in Wenatchee for the night. So again, this Spot Trace unit was, you know, half and half. It was kind of expensive. We have to pay the subscription fee, and it did not work during the mission, but it worked when it mattered, right? So even if you had no other tracking units besides this Spot Trace, you probably would be able to recover it. So, like I said, this was about a half, you know, 50-50. All right, so let's turn our attention to some of the media data that we acquired. Namely, let's start looking at the Canon S100. Remember, so this was our still camera that we had on a time-lapse setting to just shoot pictures every once in a while. So here's the data set we collected. You can kind of see this is when the kids were getting it ready on the ground. And I think this was, let me go and take a look at this picture here. You can see, yeah, started, we took the picture here at 12:52, so a little bit before launch. You can see all these are launch pictures. So we basically started the camera going and we just left it running as we ran through our launch procedures. And then right here is where we're getting ready to launch it. In fact, we can take a look at this picture. So yeah, looks like someone has their finger over the camera. But here's the next picture. It looks like one of the parents is sitting there getting ready. And then look at this, we're getting ready, and here we go, we're off. So look at this, it's kind of working, right? So here's one of the photos taken from the Canon camera as the balloon was ascending, and we go up a little higher, and look at that! So we're getting some nice pictures up at altitude, and again, these do look pretty nice. You can see, you can zoom in, we've got some pretty good resolution. Look at this, you can see some cars on the bridge. So, you know what, let's just keep going up. So here we go, up, up, oh, now we're getting into the clouds, up, even higher. Look at this, this is looking pretty great, and unfortunately this is the last picture we have. So this also didn't work the way we wanted to. This is the last picture. So if you look at this one here, for whatever reason, you can see we only collected about 30 minutes before, for whatever reason, the camera just shut down. Now, I don't know what was causing this, because, you know, we tried in ground testing before. Let me show you our little test matrix that we did. So we did many runs here with different batteries. We even, you know, did cold soaks in the freezer to kind of emulate the environmental conditions. And you can see in all of these cases, the camera lasted more than a half hour. Some of the worst cases were some of these bad batteries. So that, you know, 45 minutes of pictures, so we didn't keep that. But the battery we ended up flying with was this battery. And you can see in all of our ground tests, you know, they lasted, look at this, 4 hours, almost 5 hours. So it should have worked, at least based on a lot of our ground testing. I just don't know what went wrong. So long story short, unfortunately, we were hoping to get some of these really neat pictures where you could see the inky blackness of space in the background, but unfortunately, this is the best we got. We've got a hazy picture in the clouds up at altitude. So again, this is something that I think in the future we might want to investigate a little bit more, but the Canon camera didn't work the way we expected. Well, how about our video camera? So we already showed some of the results from the video camera, but I think it's worth reiterating some of the main points. As you can see, the 360 camera worked really well and obtained some really beautiful imagery. We already looked at some of the highlights, and I'll leave a link in the description to a full unedited version of this flight so you can watch that if you're interested in, about 37 minutes of balloon footage. The main problem was that we didn't actually capture the entire flight. As I mentioned, we only got around 37 minutes of footage. Now, unlike the still camera, this wasn't because the battery failed. Instead, this was because we forgot to erase the SD card before launch, and as such, the SD card was actually already 78% full. Therefore, it only left us 22% of the card available for recording the actual mission, which translates into around 37 minutes of footage. So again, this was due to our oversight when we were developing the checklist. So again, I'll just flash this up again for reference, and you can see we don't have a step here to explicitly erase and format that SD card before we get started, and we really should have done that before we launched. In our ground testing, we were able to record around 166 minutes of film before the card filled up. So if you recall, the actual mission here was around 150 minutes, so this would have been perfect if we had started with an empty SD card. So, oh well, live and learn. This is something we're going to have to improve in the future, and we will modify our checklist for the next iteration. All right, so here we are. We've got the recovered payload, and I thought to kind of close out our results section, it might just be interesting to look at this and see how did it fare. Now, of course, this is several months after we recovered it. It's been stored, it's been sitting around, but you know, for the most part, this is actually not too shabby. In fact, you can even see when it came down, and I think it kind of landed on this corner. You can kind of see how the styrofoam is a little bit compressed, but really, it's not too much worse for the wear. I mean, yeah, sure, the antenna ground plane is a little bit bent, and yeah, we've got detangled the parachute and the radar reflector, but overall this worked out surprisingly well, and we were able to recover this, and I think we can even use this again if we wanted to in the future. Okay, so after all of this, it might be interesting to look at the estimated cost of this entire operation. And this is a little bit hard to estimate because, as you saw, there were a lot of activities and expenditures that were not critical to the actual balloon launch. So, for example, right, we did an entire extra sort of test balloon launch and inflation, which required a whole nother balloon, another cylinder of helium. There was a lot of preparation and learning that was done. So we're going to exclude a lot of those costs. And instead, I just want to talk about the costs that were needed to basically recreate this setup. So, for example, if you were interested in doing something similar, what might you expect to have to spend to build some of these components? So here's a bit of an itemized list. It's again not accurate. It's the best that I could do, and you can kind of see that. For the most part, it was it's literally kind of nickel and diming you. So in the sense that, you know, the GPS logging system that we made out of the Arduino, that was about $75 of parts and components. The APRS tracking system was a little bit more expensive, not only because we had to build the components that went into the tracking unit that was carried on the payload box, but also we had to buy a radio and a special cable for our ground station. And again, I'm going to assume you have a laptop, so I'm not going to include the cost of a laptop in this estimate of about $225 for the entire APRS tracking system. Again, that's the part that was flying on the vehicle as well as components necessary for the ground station. Then again, let's continue talking about our tracking system. So again, that spot trace unit, I think I paid about $75 for the actual unit, and then you have about a $10 a month subscription fee. So, you know, after taxes and things like that, that's about $100 to get that spot trace unit working. The cameras, that was also a little bit kind of expensive. So that Canon S100 is not super expensive. You can find them on eBay for pretty reasonable, but the 360 camera, depending on what version you go with, that could be, you know, anywhere from, you know, $200 to $400. So let's just call all the camera gear on board around $250. And then things like the flight vehicle, as you just saw, the box, the acrylic dome, the parachutes, the radar reflectors, all those miscellaneous monofilaments, things like that. That's probably around, my tally is around $360. So all in all, I'm sure there's a couple of dollars I missed in there, or maybe went one way or the other, but overall, you know, if you start talking about the helium and everything, we're talking about a little over $1,000, surprisingly, for all of this. And again, you saw it's nothing huge. There's no major big ticket items, but by the time you add up all of these tiny little components, yeah, I mean, it is non-trivial, right? It does add up. So if we were to do this again all the way from scratch and we had all the information, we didn't need to learn anything, and we can just go in and build these components and execute the mission, I think it's probably north of $1,000 is what we were looking at. So I know what you're thinking. This is kind of a lot for a science club adventure, and I would kind of agree with you. And I wanted now to take this moment to actually say thank you to the supporters on Patreon. So some of you may know that I have a lot of videos on the channel on science and engineering, and there are a lot of supporters that I've got on Patreon, and we take 100% of the money and finances that we obtain through Patreon, and we actually direct it towards activities like this. So it's STEM activities for kids and young adults. So again, thank you to all of these Patreons who have contributed over the years and have helped support and fund activities like this for the kids. So again, I can't say thank you enough. You're making a huge impact on kids in terms of sparking their interest in STEM and science and engineering. So thank you, thank you, thank you. We couldn't have done this without you. All right, so to start thinking about wrapping this up, I just wanted to say, you know, this video has actually been a long time in the making. In fact, if you start the clock from when we started preparing for the launch and then measure all the way until the time it took us to analyze all this data and make this video, it's actually been over a year. In fact, come to think of it, this might be the video that I've spent the most amount of effort on in over 5 years of making videos on YouTube. And I know what you might be asking right now, right? It's over $1,000 of expenditures at least, hundreds of hours of work. And you might ask, is this worth it? And to that, I'd have to say, absolutely, right? This was a great experience, both for me and for the kids. It was the perfect platform to learn about things like aerospace engineering, software development, flight testing, logistics, mathematics, natural sciences, and countless other STEM subjects that were both familiar and new. So, in fact, this has actually sparked a lot of engineering interest in many of the kids, and we've now got a science club running, and I'm eager to share some of these projects with you in future videos. So, with that being said, I think this is probably a great spot to leave it. I really hope you enjoyed this video, and if so, I also hope you'll consider subscribing to the channel. If you click subscribe on that little button down below the video, it really does help me continue making these videos. And remember, we're going to have new videos on this and other topics coming out pretty much every Monday, so I hope we'll be able to catch you on one of these future discussions and we can all learn something new together. So until then, I think it's time to sign off. I'll talk to you later. Bye.